Cool. Okay, here we go. So I will start with this image. I will start off with the map because I'm pretty sure that first of all, this is called the two-pole flat Earth model. We spoke about it a little bit last night, but I'm gonna recap everything that we said for everyone here. So this is the model. It kind of looks like this. It's not very accurate. The land masses are not exactly the way they should be, and I think it's very important to know that there's a huge difference between a map and a model, right? For example, the AE map, the Gleason map, these are all maps. It's just it tells us how the land masses look like. It's a survey, it's a land mass survey, and it's a job that it's the cartographers would have do that, right? So Gleason was one of them. He believed that the Earth was flat. He made his surveying, and he becomes famous. And later, uh, some call that map AE map, the azimuthal equidistant map, which is another name for this map, for that map that we already knew. So that map is just a map, okay? It's not a model, and these are two different things, right? So as a flat earther, I think it's so important for us to look for the model, not for a map. Map is important because it tells us that it kind of like reveals the topography of the Earth. That does it have a curve? It doesn't have. So yeah, that's important. And I think that we should have conceded this point that the Earth does not have a curvature. It's stable and stationary based on all these maps that we have and all the observations. And that I think that's enough for a flat earther to uh, to concede to it and move to another level of understanding the whole model. Because when we're talking about a model, we're talking about everything. We're talking about the physical realm, the upper realm, the inner realm, the celestial bodies, the magnetic field, the everything on it, the fabric of space time around these polar vortexes that we have in this two-pole flat Earth model. So these are the things that we're going to cover, and we're not going to cover about like how the flight path going to work on like how Sydney San Diego flight would have looked like on this map. We know, and we by far we know that most of the map do have problem to explain a lot of the flight path, right? The globe model had its own problems. Some of the flight doesn't make sense in the globe model. Some of the flight doesn't make on the AE model, like the Sydney San Diego, especially these southern flights. So yeah, even in this two-pole flat Earth model that you see in my profile, that some of you guys are familiar with it, even this one doesn't really sometimes doesn't make sense. So, and I think that it's not important, right? And as I said, and I'm going to repeat myself over and over, as long as we know that the Earth is flat and stationary, it's enough. Knowing the continents, which one is bigger, which one is smaller, which one is next to the other one, like these are not very vital. Okay, it's not. Like as I said, uh, it's a flat surface. That's it. We know it's flat. We know it's stable. We know it's stationary, and we have experiments for that. We have hundreds of experiments to debunk the curvature. We got the Michelson-Morley experiment to debunk the spin of the Earth. So that's it. All I'm trying to say that don't trying to be so don't stuck yourself to the maps. Okay, we're not cartographers here. We're flat Earth modelers basically. So that's why I have chosen this map, which is a kind of a little bit close, I think, to the reality, and it's a polarized map basically. If you look at my profile, so let me just change this picture to another one which has the things over it, north and south. Yeah, this one. So as you can see in this map, we have two poles. We have the north and we have the south. Uh, and you can see that we have the east and the west direction. So again, in this model, we can perfectly have east and west, and also the south as a certain fixed point, not east and west, but the south. So the whole difference between the AE map and this two-pole Farris model is that what we did, we have polarized the model. We added another pole to the model in order to explain a lot of things that we couldn't explain to the other on the other map. So as you can see on my picture, uh, you got the north on the top, you get the south on the bottom, and these are two uh, magnetic poles, right? These are two magnetic poles that you have, and correspondingly, exactly at top of these 2 points on the ground, you have the Polaris on the north, and you have the Octant Sigma constellation in the south. So basically, these are two kind of star systems that you have above these two fixed points on the ground and in the sky, north and south. East and west is going to be just a direction. It's not going to be a certain point. It's going to be just a biased movement. Okay. So this is like how kind of it looks like, right? And as you can see, you have the Asia on the right and the east, America on the left and the west, and north you have north and south you have Antarctica. It kind of resembles the reality. It's not very perfect. Some of the flight path would not make sense on this map, but it's not important as I said. Okay, it's just I could have put up any arbitrary landmass over this two flat Earth model, and I could have just go on and not just think about like how these continents, these countries and these continents look like. And it's not really important. It would be like if you start counting the stars in the sky, has no scientific value, right? So here's another kind of a representation. This one is it's a demonstration of the sun path over this two pole flat Earth model. As you can see, instead of having one bunch of concentric circles around one pole, you have two bunch of concentrics around two poles. And the reason that it looks like this is because this is a two pole flat Earth model. It means that the sun path would have spent its time like 6 months around North Pole, going around North Pole, and equally 6 months around the South Pole. And it will, if you look at this image, you can already see the analemma as well. But it's the major shape of it. So for example, if you look at the image, again, if you look at the concentric circles above on the north, they're like 3 or 4 circles you can see. You can say that every of those circles are the sun monthly orbit, right? Like so from May to uh, June, July, and like you can look at these circles like every month on the north, and exactly in the opposite side, the south. Every of those circles would represent the winter month, like January, February, September, right? So this is kind of what we did. We just split that model into two sections and letting the sun just go around both of these 2 points. And by doing that, what you're going to do is that you're going to let the sun to go in the south part of the world and make exactly the same movement that it was doing in the north. So of course, yes, this is the symmetrical thing that I wanted to say, and I'm sorry that I didn't use this terminology because this is the most important feature of this two-pole flat Earth model. It's symmetrical. And I will tell you that why it has to be symmetrical and why the world or the reality that we're living is symmetrical. The way that your body or any living being is symmetrical. So let's move on to the symmetry. Okay, look at this image right now. Now you probably have seen this image in the net or in this flat Earth community so much. Uh, as you can see, these are the star trails, and these star trails are uh, the path of the stars over the time. This image, the observer is on the equator. He went to the equator. Equator is on the equator, and the observer is observing toward the east, and it's just taking a time lapse picture from the star trails. And this is what you end up with this image you see. Now, this image is so important. Some of you guys have probably have seen it, but never pay attention enough to it. So I want you to look at this image and just notice the symmetricity. Just look how these stars are symmetrical, how they look like. The star trails on the right, they more tended to deflect to the south, and the left, it deflects it to the north, as you can see. And the more you go toward the north or south, you see you have more severe deflection. And the more you come to the middle, they appear to be more straight. So I would call this the fabric of space-time on our flat Earth model. Now, just remember that it's not always the Globers who can use this terminology, the fabric of space-time or the space-time curvature. Well, we also can use that, and I think that flat earthers can perfectly use this terminology because they have evidence for that, and the evidence is on my picture. This is the curvature of space-time. Why? Because this is the path of the sun, stars, and everything in our sky. So that's it. That's the space-time. So you can call it space-time. So this image, this star trails are the representation of the the fabric of space-time. And why? Because the reason is that we can see the stars are exactly going in this manifold, basically, in the sky. Now, uh, as you can see, the south and north appear to be on the ground. Well, you guys are probably flat earthers. We all know about this, that they will appear to be close to the ground because of these thing that we know. We flat earthers are very good at it, which is called the personal sphere. And personal sphere is something that is related to your visions. This is how we see things. This is how our eyeballs are rounded shape. So it will gather the light in a rounded form. So we would see like sphere. This is our vision. It doesn't mean that the objective reality is like that. This is so important, right? So if you look at my image right now, as you can see, uh, the equatorial celestial sphere or dome of vision. This is another terminology that flat earthers kind of using it. Dome of vision makes both poles appear subjectively close to the ground, whereas they are actually on the sky ceiling. Yes, like we know that we're flat. All the flat earthers know that as you start moving to any star, it will start to move up. So right now on this image, let me just come back. Here we know that like the north and south, the Polaris and the southern star, southern point, are on the ground, appear to be on the ground. But we know that as we start moving toward any of these 2 points, they will start to move up and come to our top of our head. Right? This is how our vision works. We know about this. So I don't want to say that the firmament or the dome thing that you have in your mind, it's not a spherical or hemispherical shape. All I'm trying to say is that we don't have any evidence to tell us that the firmament is a domey shape, or is a dome shape. It, all I'm trying to say is that it appears to be more flat because no matter where you go, all the stars, as you start getting close to any star or any point or any object, any celestial body, that object will start to come over your head. Okay, this is so important. So we don't see any edge of this firmament on the ground. So here's a simulation of this this observation on the equator toward the eastward on the Stellarium software. I recommend everyone to use this. So this software is very accurate. We, we can learn a lot out of it. We'll learn a lot of things. And one of the things that you can do with it is that you can go on a different part of the world and look at the sky. But what we did here, we just put the observer on the equator. And why the equator? Because the equator is the middle of the Earth. It's the middle. And why we're saying it's the middle? Because everything will become symmetrical with respect to the equator. For example, look at the star trails here or here in the Stellarium software. Look at the counter of the stars. It's symmetrical with respect to the equator. So back to the symmetry. The symmetricity of this reality is the most important thing, and it's one of the most important feature of this tuple flat Earth model. It's so important. So and here's another image that you can see that equatorial celestial sphere. on this observation. Yeah. So basically, this is a video. I just took some screenshots of it, so it's animated. And if you look at the whole video, I'm gonna put the video for as well. You can see that these star trails are kind of moving around these two centers, the north and south, like like a wheel of a car, like something that you know, exactly like the tires of car. You have these star trails, bunch of them on the right go on the south, bunch of them the other on the left, they go around the other pole, and the one in the middle kind of they look to go, straight, but they will diverge and they will split. Some of them go around the north, some of them go around the south. So these stars which are exactly on the equator, they're gonna exactly start splitting at the end of the model, and they will turn back toward each other from the east. So from the west, they will diverge, and from the east, they will converge. The constellation, the zodiac signs, which are exactly in the middle. I'm talking about these straight lines in the middle. The lines in the middle. The lines in the middle are the zodiac constellations. In the north, you have the Polaris. In the south, you have the southern point, and you have these stars that symmetrically they go around these 2 points. So standing in the middle of this model, which is the equator, will give you a very good vantage point that you can see the whole thing, this entirely, like the south and the north. So this is the symmetry that we have in the sky for star trails. Now, the other thing that is so important on this model is that the sun path also has a symmetry. If you remember this image that I brought up here, as you can see, again, in respect to the equator, the sun is making a symmetrical path. Is making a 6 month or movement above the equator around the North Pole, and then do a transverse movement on the south, and make another 6 month rotation around the south, and comes back up again, and creates this analemma. And if you think about it, this is the only model that you can have the analemma, because the analemma will always have two centers. That H shape, no matter where you go, as always has two centers. And here's another point about sun analemma, which I think is very worthwhile to say it. The sun analemma, the shape of the sun analemma is subjective. It means that it depends on where the observer is looking at it. A lot of flat earthers would have think that the sun analemma would have always looked the same, like it has a bigger lower lobe and a smaller upper lobe. Well, it's not always like that. That's wrong. In reality, if you go, like, for example, on the observer who was on the equator here, if you would have stayed for 1 year, and you would have taken the pictures of the sun, let's say from like every day 12 o'clock till 12 noon, and if you would have created sun analemma, he would have ended up with a shape which is symmetrical. It means that it would have had the lobes of his analemma would have been the same size. So basically, this is a fact on an equator. The sun analemma would have looked symmetrical, or in other words, you can say that the lobes of the sun analemma are the same. They're going to be the same size, the upper and the lower. And as you move toward the north, the lower lobe becomes bigger, the upper lobe becomes smaller, and vice versa. If you go south, the sun analemma. So in Australia, if you look at the sun analemma, it's kind of inverted, and in the equator, it's symmetrical. Now, if you go exactly like stand on the north, like under Polaris, in the North Pole, and if you look at this, if you just make a picture from the sun analemma of the sun analemma, what you're going to end up? You're going to end up with an elliptic shape. And exactly, if you go on Antarctica and stay there for 1 year in making the analemma image, you're going to end up with an elliptic, exactly elliptic again. So in north and south, the sun analemma would have looked the same. And as you move over to the equator, they're going to look the same, but they're going to be inverted symmetrically. And eventually, when you hit the equator, they're going to look the same, the lobes, like this. So this is the major shape of the sun anelima, basically. So what you can do on this image, you can take one time per day, or let's say, yeah, just one time per month. That's just a rough thing that you can do. But if you want to be more accurate on this model, you have to draw 365 circles, like 182 circles above around the North Pole, 182 circles around the South, and let one day to do the transverse motion. Now I want to talk about this transverse motion because I think that a lot of people have this problem. This is the thing of this model that a lot of flat earthers they didn't take it very correctly. Some of them would have they still think that in this model the sun would have disappeared from west and it appears from right, like the Pac-Man game that we had. But it's not. It's not like that. It doesn't do that. It just goes through this transverse movement that creates the annealing or the H shape. So uh, look at this image. I just put some arrows. Let me just, here is it. Yeah. So September 23, for example, this is a very crucial day that, actually it's the equinox day. So as you can see, the sun will move from east, and that will be the east direction. So east, as you see, it's not a certain point. It's the direction of the sun toward our reality or toward the land masses that we know. That, as you can see, that it's hitting China and Japan from east. So that is coming from eastward, coming down, and it will become like this, as you can see. Now, this motion, this is the transverse motion that we're talking about on the equinoxes. That it will go, so everything would have looked the same, like the AE map that you had in your mind for the first 6 months of the year, right? And then when you hit the equinox, you want to hit the winter, the sun will smoothly make a transverse motion. And what I mean by that is that you can just use the star trails, and this is what I always tell people to help them to visualize it. See, look at the star trails here. I can tell you that each star trail is a one path of the sun during one day. So if you remember, I said that you have to draw those 365 circles because this is what we believe. We believe that the sun is making a circle, is circling the earth, right? So it's making circles. It's making 365 circles basically in 1 year. So draw them. If you draw them, right, it would be like this, this image. Now, if you put the observer in the equator exactly on this image that you see those in the concentric these lines, these concentric circles, they become more concentrated on the equator. This is the thing. This is what we see. Here's it. Look at it. You can see this is your reality. On the equator, it's more concentrated. You got more stars over there, right? And on the north and south, you see it's less, right? So in the middle is the most important part of this model. The middle is going to be the middle of your toroidal field. Later, I will tell you that why the equator is the middle of the toroidal field, not the Polaris. Just bear for a second, for one couple of minutes, then we'll head there. So, as I was saying, each of these star trails can be one of the sun's path over one day. Now, as you can see, the star trail. So what you can just imagine here, you can imagine this when you're kind of going from winter to summer, or summer to winter, the sun would have started picking each one of these star trail or these curvature path. These are, as you remember, I said these are the space-time curvature lines. It's a star trail, but it's showing us the counter of the space-time over our head, right? And we can see that the sun is going through these lines. You can check it by yourself. So you can also see in this image the sun anelima again. You can see that eighth thing on the south and the north. You can see there you have two kind of a circle things in the middle. They're kind of a straight. So what's going to happen during the equinox? The sun will start moving from left to right on this image. And imagine that the sun would have start picking one of these star trails or one of these, lines of fabric of space time in one day, and it starts moving from the north to the east, and it will just pass the equator. It will pass it so smoothly. So the day on the 23rd of September, the sun would have picked like exactly that middle star trail that you see in my image right now, the one that is exactly on the east. But it would have taken probably the one before the middle, and the day after the equinox, it will take the one after the middle. So the difference is very, 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 very small. The transverse movement or at the equinox is going to happen so smoothly. It's going to happen daily. So, and this is the most important, I think so far the problem that a lot of flat earthers have with this model. That how does this transverse movement happen? It cannot be a sudden change. Well, it's not a sudden change. It's a very smoothly, movement. So as I said, just imagine those star trails in the middle. Those going to be the sun track per day, and you're going to start having a little shift from north to south. That's it. And and that will be your transverse movement. That will be your shifting from south to north, and again from north to south. So and this is how it is because the sun path has a symmetry respect to the equator. And this is what the globe model has. The globe model, the sun path has a symmetry with respect to the equator. That's why the day and night would be, or the day length respect to the equator on two opposite points would always be the same, or it will be kind of the day length and the night length will be the same. So basically, you have a symmetrical pattern on the globe model, and this two-pole flat Earth model, you still have the symmetry. But on the AE map, we didn't have the symmetry for the day length or for the sun path. Well, basically, the day length and the sun path are corresponding. So if you would have a symmetrical, sun path or your flat plane, you would have a symmetrical day length with respect to the equator. Or if you have a, symmetrical day length, and what I mean by a symmetrical day length, I mean that if you choose two opposite points across the equator, let's say positive, like 30-degree latitude, positive 30 degrees, minus 30 degrees, right? These are going to be two symmetrical opposite points respect to the equator. Now, if you check out their day length and their night length are symmetrical. It means that, for example, on winter, that city would have had, for example, 14 hours daytime, and exactly 6 months later, the other city would have 14 hours day length. So this is our reality. This was the thing that happened in the final experiment. In the final experiment, well, some of the, I don't want to disrespect those flat earthers, but that was obvious. What we knew it because we already know that the day length from the equator starts to look symmetrical. Like as I said, any 2 points, positive and negative, if you check them, if you compare the day length, they're gonna be exactly the same. So by knowing this, we could have already concede that there's going to be a 24-hour sun in Antarctica, the same way that we have a 24 hours sun in Arctic on the summer solstice, on the winter and summer solstice. There's no difference between the southern point and the northern point. That's the whole point on this model. There's no difference. We're not going to glorify or we're not going to worship the Polaris here. We're going to look Polaris as one of the poles, and we're going to see, and we are observing another point in the sky, another fixed point in the sky, basically. Which respect to the equator, they look symmetrical. The star trails look symmetrical. The focal pendulum looks symmetrical. The day length looks symmetrical. The sun path is symmetrical. So why I'm trying to say the symmetry, because the symmetry is the most important thing on this model, which is respect to the equator. And it's what we were seeing, is what we're really seeing, basically. So back to the day length. The 24-hour sun experiment that happened in Antarctica was expected for a real flat earther because he already knew that the sun would have exactly behaved the same way that it would have do in the north during the summer, and it would. It is. You can pick that out, and the Globers proved that to us, right? But they helped us. They helped a lot of flat earthers to become more, understandable about that. Okay, the South needs its own, point. It will need its own certain fixed South pole in order to make things happen there, in order to make the tropics look symmetrical. As you know, the globe model, it looks symmetrical. Respect to the equator, the tropics are symmetrical. Tropic of Capricorn and Tropic of Cancer are the same size in the globe model. That's why they're closer to the reality. This is regardless to the shape of the Earth. Okay, as I said, we don't want to care. We don't care about it. The physical realm is flat and stationary. That's it. But the globers are pretty more accurate when it comes to the sky and the polarization because their model is symmetrical and they can explain the day and night. They can explain the 24-hour sun. So we flat earthers have to do the same thing. Therefore, what you can do is that you can look at this way. Look at this image here. Yeah, this is like Geo kind of shared. It's a very good one. This uh this is a two projection of the sphere basically. The one on the bottom is the AE map. It looks like the AE. You can only cover half of this reality. So some of you guys would say that, well, why you're using a sphere to prove your thing. Well, I'm not doing it. I'm trying to say that from a globe perspective, from a person who believes, the globe model, the AE map would have only covered its half of its reality, which would be the bottom. Probably you can have the North Pole, you can have the South Pole on that projection. So basically, the azimuthal equidistant is the projection around the North Pole. So you're going to look like that. You can do it in the South. You're going to get another shape. Probably the landmass is going to look a little bit different. The landmasses on the South is going to be more accurate because you probably guys know the Gleason. Look, these are good things of Gleason. Gleason is a good map. We're not against it. Gleason is it's pretty accurate when it comes above the equator. The land masses, the size of it, they're pretty accurate, right? But when it comes to below the equator, it's kind of it becomes messy. But you can have another projection around the southern point, and then you can have a better accurate, representation of the those land masses on the ground on south. So you would need to use two projections if you want to use the Gleason type of map, right? Because you cannot cover the whole thing with it, as you can see in this image as well. But the stereographic, projection that you see is on the wall. That projection is covering the both poles, and this is what we're doing here. We just want to look into from a different perspective. That's it. We're not changing a lot, and I'm telling you, I'm gonna prove that to you. This model, it's not different from the AE map that you had in your mind. All you're gonna do is that you're gonna change the center. Instead of putting the center in the Polaris, you're gonna put the center on the equator. And you're gonna lay it down. You're gonna lay it down, stretching from east to west. I'm gonna hit to that. I'm gonna help you guys to understand that very much better. But back to this image, as you can see, the projection, the stereographic projection, is giving you the both poles. It's giving, as you can see, you have the both poles. And if you can see right now, if you remember, you can see the star trails here. If you have learned what I said, you can see the star trails, and you can see the magnetic flux. So if I want to help you, those two are if you look at the stereographic projection, it will be this. Okay, I just rotated 90 degrees. This is that space-time curvature. This is that star trails. I want you to understand this image is this image. This is this. Okay? So north and south, positive, negative. And if you look at the fluxes, the red lines, you can see the magnetic field, right? Those are the red lines. Those are and look at the purple ones. The A field, field A, equipotential lines. Later in another session, we're going to talk about this mathematically. That what they mean. What do they mean? They mean that they're perpendicular to the magnetic field. When you say equipotential lines, so any magnetic field that you have, any magnet that your heart, which has a biomagnetic field, a magnet that you have on your table, anything, right? All of them, they have their magnet. You have your flux, and regarding to that flux, you can have a perpendicular field, which is called the equipotential field, which in our case would be the tropics. So I'm trying to say that the star trails are, or the basically the star trails or the tropics are the purple lines, are the lines that are perpendicular to the magnetic field. So here in this image, you see these are the equipotential lines. These are the lines of the movement of the particles, which is perpendicular to the magnetic field. So, so on this image, if you draw the magnetic field, right, they're going to be exactly like these star trails, but they're going to be perpendicular to it. Okay? They're going to be perpendicular. So if you do that, if you draw it, you're going to get this image. So the positive is Polaris. You can look at it as Polaris. The negative pole, you can look at it as the southern point, whatever you want to call it. And don't stuck with names. Like, just leave the names away. And this is what happened to a lot of flat earthers. Unfortunately, they have married with the Polaris. They think that, well, Polaris is not the center. Polaris is also going around another point. And Polaris is not one star. There are a bunch of stars that are called Polaris. Polaris A, Polaris B, Polaris C. It's not just a one big shiny star. Like, they kind of think like a cartoon. And a lot of flat earthers would think that if we were talking about the southern point, we need to have a star in the middle of the southern point. No, you don't need that. This is not a Hollywood movie.
Oh,
Your
real quick,
eyes
are you
see.
doing questions now
Go on.
or later?
Okay, we can do questions. Good, Jeremy. We
I,
can do questions. Yeah,
I mean,
I think it's enough.
do you want me to wait or I
I
could
think
wait?
we just covered a lot. Let me just take a look. I'm almost finished. So, and this one, because later I want to hit to the tutorial field that we have here. But I think there's a lot of things that we need to cover. But step by step, it's way better. So I think it's better to stop here. The thing that we said about the fabric of space time, the curvature of the thing that we see in the sky, the star trails, the symmetry of the sun, the symmetry of the star trails, the focal pendulum. Later, I'm going to talk about it. That why it has a symmetrical behavior across the equator. Uh, and the magnetic field that we spoke about here, which is perpendicular to the star trails. So, uh, oh, here is it. As you can see, we have the both lines on the stellarium. So on the stellarium, it's a good thing. As you can see, you have the magnetic fields. So the magnetic fields are those lines that are connecting the N to the S, and the ones that are perpendicular are the star trails. Here, in reality, this is the fabric of space-time. This is dynamic vision. This is a video. If you see it, you can see how later we're going to talk about these fractals that happens in the vortexes. But yeah, I think it's enough for here. So let's have some questions and see what you guys have in your mind. Go on, Jeremy.
Do you have a picture of can you pull a picture up of what the sun's doing at the equator at an equinox?
Yeah, yeah, exactly. Good question. Yeah, yeah. Here's it. Okay. So so let me share the video first, but I'm gonna put it so look at this image, Jeremy. Yeah, this one's better. So this is a sun path during the spring equinox. So this is what the sun does during the equinox. Now this is a video. It's gonna be it's a 7 minutes video. You have to go minute 5 or minute 6 that you're gonna have this, you're gonna see this the whole period. That's how the sun would have started moving from south to north. So as you can see right now, that shiny star, that shiny point, and that's the sun. It's making it's and if you look at the video or if you do it by yourself, and you don't need to do it by the video. This is what I've told to you guys. You can go to Stellarium, put the observer on the equator, like Ecuador or Ania, and then start moving the time cursor and see how the sun starts to move. So and you can just crank your head upward. This is what I did. This is like the person is standing on the equator, standing exactly on the equator, and is looking exactly at the top sky. He's looking at the ceiling, and he's looking so big, and he can see how the sun starts moving from its across the sky from east to west. Now, if you play this video, what you're gonna see that you're gonna see before we hit the March 20, like March, like you just look at the date. The date here is the 2nd of March here. So I just started from the 2nd of March all the way to the 30th of March. And as you can see, the sun would have start making bigger circles, and eventually it would have made a very big circle on the equinox. And in the day after the equinox, it will start making big circles around the north instead of making circles around the south. You can see that by yourself. That how does this rotation of the sun from south go moves toward the north per day? So you're gonna see the nighttime. Now you're not gonna see the whole that whole you know uh, course of the day because you can probably see 12 hours of the sun. But if you see that 12 hours here, you can see it with yourself that as you move toward the spring equinox, the sun will start making very big circles around the southern point, and eventually, on the 21st of March, it will start making a very big circle around the north. And this transition happens so smoothly, and you can use the software to see it by yourself. So
Yeah, that's the thing. It
let me just
happened so smooth that
that
it happened
yeah
so smooth
yeah.
that on the equinox, it's not turning left or right. You know what I'm saying? It's not doing any circles. It's just
So
going
do
in
you
a
think it's
straight
not?
line, right?
No, eventually we know that is making a circle. Why we know that? Because, for example, in Antarctica final experiment, we have seen it by ourselves, and in the Arctic or in the southern part of the world, like in Sweden or in Denmark, if you go there, you can see that the sun is in the sky for 20 hours, and you can see that it is going around you
I know,
during
but
summer and doing yeah.
I know
So
what I'm
basically, it
talking
is
about on the
always
equinox at the equator.
at the equinox is not different. The one day before the equinox, let's say that will be the 19th of March 19th, right? On March 19th, the sun would have make very, very big circles around the south. It will really go around the south the same way that it was going around the south on the 24-hour sun experiment when they went there, like 4 months ago. So what the sun was making there, sun was making a very small circle around the southern point on the winter solstice, with that final experiment happen. And after that, within this 3 months that we actually you have it has been passed on, the sun is start making bigger circles. Now, what
And then
happened
until you're on
on
an
the ninth?
equinox and there until you're on an
Yeah, on the
equinox
equinox.
and then there is
Yeah.
no circle. It's not turning left or right.
How do you know that?
Load up your stellarium thing. Go on the equator. See if you see it turning
Well,
left or right. It's
stellarium
just going
doesn't
to go
show.
in a straight line above over your head.
Well, stellar over your head.
Yeah, it goes over your
Yes, over
head.
your.
Like you could have
Yes,
a
over your head.
you could
It's
have
over your head.
a th-
It's always over your head.
yeah. If you
That's what.
look,
That's the
if
point.
you're looking east, right? If you're looking east, it rises up, goes directly over your head, and sets in the west. Like it's like 180 degrees. It doesn't turn left or right off of that thing, off of that plane or whatever.
So instead of about stellarium, you have to think it's not very accurate when it comes to this point. But you can see, like Okay, let me just share it with this, you guys. Just watch this video and tell me what do you see. Where's Discord? Okay, here is it.
Like if you had a thing, like if you had something on the ground that could only turn in one axis, and it was the east-west axis, and you're on the equator on an equinox, it would just do that. Like you could have the sun in your scopes all day without turning left or right.
The sun would have turned left or right like the focal pendulum. Everything moves turned left to right. As it moves toward the west from the east, either it has to go around North Pole or South Pole. For example, if you look at this image that I brought up here, the star trails, do you agree? Here's the thing. Do you agree that all these stars will eventually go around like a point? Do you agree with that?
No,
Yes, you agree.
the ones in the middle on the celestial equator, they're not turning left or right. They're just going in a straight line over your head. That's what I'm saying.
No, so here's the thing. Okay, let me just show. I just because you have to use stellarium and see that all the constellations either, and this is
He's
what the
gonna
why
observe
the
them.
globe. Yeah, this is why the globe model is accurate because this is what you see in the globe model. They have this in the globe model. All the constellations, even the ones that are the equator. Okay, now this is where the two-pole flat Earth model and globe model are going to be exactly look the same way. Why? Because in the both model, my brother, all the constellations eventually need to go around any of these two poles. There's no other way. It doesn't go always straight to the infinity.
Yeah, but you can never have a straight one in the middle on a flat Earth because
Hold
it'll
on,
still be
Jeremy.
going
He's saying
around.
No, we don't have that. I'm telling you, you don't have that. Basically, it's going to look like this. Let me just show
Yeah,
it to
Jeremy,
you.
he's basically saying it transitions, the sun does. So he's just saying that it's making, let's say in the south, it's making, like he said, wider and wider circles. And then it gets to the equator and it's going to appear to move as straight as you could maybe try to measure it. But he's saying it's transitioning from the south to the north, which is essentially what it has to be over a planar surface. The
Yeah, but
sky has.
but Gio, that's only true if he's trying to compare the way our sun moves compared to star trails he's showing in a picture. The star trails have
Yeah,
nothing to
because
do with it.
Yeah, yes, they do, because the sun moves on the same pathways as the star trails do. As it moves from 23 degrees south to the equator, 23 degrees north, there's stars in there. So the same path that the stars take, if you were to take a one-line path, is where the sun, would be on one day, and it keeps tracking. So yeah, they're all on. It's like if you call it's like a racetrack, and
I know, but
they're
I know,
all
but then
they're all moving in similar.
Yeah, that's
Like
not
it's
necessarily
essentially.
true.
Yes, it is. It's the latitude lines coming from the north and the south, which meet the
well,
equator.
hold on a second, because the problem with the equator is you can see it for, you can have one guy see it for 12 hours, and then another guy can see it for 12 hours, and it has to come back to the first guy. You know what I'm saying? And it's not turning enough in that whole period of the 24 hours to come back.
Yeah, I mean, there's a lot of inconsistencies here. I wrote them all down. The first one is just a two-section model that he brought up the first picture, and he shows the rings, and he said these rings or whatever. That's how the sun moves throughout the year, and it shows if you look at the top ring and the bottom ring of the how they collide, they have like two lines there. So you're saying that it would shows that it crosses over, so that would change the direction. That would be measurable and observable. I think. And it's not.
Exactly. Look at the video. Exactly. It's observable. You can see the exact thing that happens. Just look at it.
Hold on, Kasra, hold on. Your mic went kind of muffled for a moment. If you could fix your mic.
Sorry, because I was playing the video. So just look at this video. I have the transition that happens. And this is very, very nice that you guys are pointing this out because you have to nail this here. This is the transit that how the transition happens. So go to the video. This is this is minute 6. And look at the transition, how the transition happens, and you can do it by yourself, right? The sun is making circles around south before
Yeah,
March 20.
but
And
even in
eventually, so here's the thing. Sun doesn't have any other way except going around these two poles. Like no other way. Or
but
stars. This
the
is the
fact that
reality.
but even in this
Yeah.
picture though, Kasra, even in this picture,
Cool.
you're representing a north, south, east, and west in space. I mean, that just doesn't really exist.
So do you agree that we have two poles in our reality?
Those are planetary. Those are for our planet, or whatever you want to call it. Those are for
Yeah,
us.
yeah.
You
This is
can't put north,
we're
south,
talking
east.
about our.
You can't take a picture of space and say, well, there's north space and there's south space.
This is not.
It doesn't
We're not in
exist.
space. Who told you that we're in space?
Let's let him finish the
You just
presentation though.
pulled up a
Before we
picture.
get too sidetracked,
Yeah, that sounds good.
let's let him
Sounds
finish
good.
the presentation. All right.
Yeah,
Yeah.
Kasra,
So yeah, I can
yeah.
what you're saying. Yeah, yeah. So basically you have two poles. You cannot deny that, right? You have two, like your magnet. Every magnetic field has two poles. Your reality, your magnetic. The Earth has a magnetic field. It has to have two poles. And
Absolutely. But what
yeah.
does it form?
So here's what do you say?
No, go ahead,
Just
bro.
let him finish.
Yeah,
Yeah.
no, you
Let him
got the
finish the.
you got
So
the
yeah,
floor. Yeah, go ahead.
yeah, sorry. No. So I just want you guys, really, I really want you guys to answer all your questions. So basically, look at this image. You have this magnetic field. The red lines are the blue lines are in a magnetic field. We guys are familiar with that. We do have them. And as I said, you can see the red lines. The red lines are perpendicular to these magnetic fields. And what are they? Do we have them? The electromagnetic, studies. Yes, we do have them. We know that in the like the Lorentz law, or the right hand law, what you know that the magnetic field, the electrical field, and the movement, or the particle velocity, are all perpendicular to each other. So when I have my magnetic field, like those blue lines, right, I would have had two other directions that would be perpendicular to this magnetic field. And I will later tell them what are they. One of them is these tropics, the star trails, the movement of the sun, the movement of and why they're perpendicular to the magnetic field, because this is how it works in reality. Like in the magnetic field and electrical field, and the velocity or the force are all perpendicular. It's called the right hand rule. You're going to open up your index finger, your thumb, and your middle finger, all perpendicular. One is magnetic, one is electrical, the other one is the tropics or the movements. So this is our theory. We're saying that the ones that are perpendicular to the magnetic fields are the tropic, or are the movement of the particles, or the movement of our celestial bodies. These are the tracks of the celestial bodies. So in my picture, look at my picture. The red lines are the star trails here. This, right? The same, and this. These are the red lines that I had before. And they're exactly, I'm telling you, this is what you see in your reality. Look, it's not, I'm not making this up, Paul. Look, I'm just seeing this. We're observing this. We're observing the star trail on the equator, and we can see they're perfectly perpendicular to our magnetic field. And beautifully, the electrical field will be perpendicular to both of these two. That would be along with the gravity. So I don't want to go into that. That might be a different session. That would be very awesome that we would have time to talk about why this electrical field, or this electrostatic field on this model, is exactly parallel in the same direction of the gravity, which is from down to up, right? From ground to sky. So the magnetic field is from north to south. You can lay it on the ground, or you can lay it on the sky. And the perpendicular to that would be the tropics, or the star trails, or the movement, or the track of the movement that we spoke about them, which are perpendicular to it. And again, perpendicular to this plane, you're going to have your electrical field, which is your gravity. So you have three things here: magnetic field, electrical fields, and these tropics, or the movement of the particle, basically. Three altogether. But that would be for later, that we'll talk about. So here's another image that kind of can help you a lot here. As you can see, if you take a picture from the star trails from the north and south, and if you just put them together, you can clearly see those concentric circles, or those tropics in the sky that we had, and you have them exactly on the ground. So these red lines that you see right now on this image are these red lines. same thing. You're just looking at it from a different perspective. This is from the top view. We're not in space. We're trying to speculate this. Okay, we don't have any space stuff. We're just assuming that okay, it's flat, it's stationary. It might have some walls like this. This is what I said. It might have some walls like this. Where is this? Like this. If you would have looked, some of the flat earthers are love to have walls and these kind of you can look at like you can have, but these are not important. Like the physical realm is flat and stationary. We're not talking about it. We're talking about the sky basically, right? We're talking about what we see in the sky. We see these two bunch of concentric curvatures around two poles, and if I put them together, I'm going to get this image, which is exactly the motion of the sun. These are the track of the motion of the sun. These red lines. Now, if I draw the magnetic field right now here on this image, it would be this image. Is that clear for you guys? So if you have any questions, go on.
Yeah, and that shows just to tap into what Jeremy had asked about the path of the sun. The one that you just showed, where that shows the straight line in the middle, then the two rotations. So there's a transition zone there at the equinox.
Yeah, at the equinox. If you just look at the video, minute 6, we can watch it together. I can play it here. I was playing it basically, but we can watch it together.
And they're going to call that, because on the globe model, they're going to claim, that's your equatorial, because, the tilt of the globe, they're going to claim is, the sun is intersecting with the celestial equator and all of that. But that doesn't necessarily mean we're on a sphere. That's just the way they describe it. And because this is essentially a celestial sphere, and so it has that same equator, that equatorial area in the sky. And they just link that to a globe Earth beneath your feet, instead of being just part of how the sky works with that center point at the equator.
Exactly. Yeah. So they manipulate it and they can make it go on.
Oh, sorry. I'm just asking, like, I don't know.
Hold on, Verdak, your mic is real muffled.
Can you hear me now?
Yeah, but I think that there was just a little pause there for like any quick comments on that. I think he's still doing the presentation. I think we'll do more question and answers after.
Yeah, my fault.
What's up to you, Kasra? However you want to proceed.
Yeah. So let's move on if you guys have any questions. Okay. So this is an image that you can see that it kind of helps you to understand that what we did here, right? And the one on the left is the two pole. And as I said, just leave the land masses. Don't try to get miss yourself with the flight path. How does it move? Does it goes from in San Diego? As I said, all the flight path, they don't make sense in any map. Neither on the globe, not on the Mercato, not on the Gleason, not on this. Don't. And it's trivial. Like we don't need to think about it. We know the land masses are there, right? It's flat and stationary. That's it. And we're just focusing on the sky, the movement of the sun, and everything, right? Because we know by far that it doesn't have a curvature. And the final experiment, they didn't debunk the flat Earth. Basically, they just debunked that. Okay, your Gleason thing that you're talking about is not correct, right? Well, yeah, we knew. Well, a lot of flat Earthers knew that before, but not all of them. But I think that it's time for everyone to just to move on, all right? Because some flat Earthers, and if they're hearing me right now, like, don't try to say that they didn't happen. They staged the whole experiment. Well, really, they didn't did it. As what I said, you can symmetry. You can see the symmetry in the day length across the equator. You don't need to go all the way down to Antarctica. If you go to like these southern cities in Argentina or in Australia, Auckland, I don't know, anywhere, you just compare the day length. And you need to go there. You just check on the website. Go on the timeanddate.com and check the day length on these on two opposite point across the equator, and you see they're pretty symmetrical, and the globe model works perfect here for them, and we need to acknowledge that instead of denying it and start sounding stupid to them more, because this is what has happened. I'm seeing that like flowers. No, it didn't happen. They had multi shadow. They didn't have a vapor coming out of that wasn't Antarctica. Bro, what do you mean that wasn't Antarctica? They went to Santos Porina. It was another city in Argentina. They already had 17 hours sun over there. So they really didn't need to go down to Antarctica. That city was about minus 59 degrees. And when they were there during our winter time, they already had 17 hours day length. So that was enough to debunk the AE map. Like, but sunflowers, no, it doesn't. Sunflowers are saying that the sun moves faster. I recently heard that, they came up with this idea to, let's say that the sun on the AE map moves faster on the Tropic of Capricorn than Cancer. Well, that's not the case. The sun never moves faster. It's always going to be 50 degrees per hour. In the globe model, it's accurate. And the two-pole flat Earth model is going to be exactly the same. It's not going to move faster. It won't move faster in the Tropic of Capricorn. It never. Because if you look at the sun on the constellations that moves from constellation to other constellation per month, and this is where astrology helps you. Some of the flat earthers are not good at astrology. Astrology tells you that, yeah, we by looking at the sun and looking at where is at, what constellation is located, you can tell that what part of the year you are. You're in the winter, you're in summer, that's the thing and we know that for every constellation, it was roughly about 30 days, sorry. Creates a 365 days, 12 days, right? So the sun's not going to move faster. Don't get yourself stuck there to think that on the AE map, the map that you see on the right, on the Tropic of Capricorn, the sun starts to speed up. It doesn't speed up. Never. It doesn't slow down. It doesn't speed up. It always moves with the speed of sound. So on a flat Earth model, right? As a flat Earther, always know in our model, which in the globe model is the same. It's a coincidence in the globe model that they're saying that the sun moves with the speed of sound. Sorry, the Earth is spinning with the speed of sound on the equator. And if you move to the north, it kind of declines and all that crazy shit that they're talking about. It's not possible to determine that. Anyway, they're saying that we're kind of moving close to the speed of sound on the globe model. But we know that in the flat Earth model, it's not a coincidence. It's the speed of sound. It's a constant. We have that. It's a sound. It's a speed that our voices reach each other. It's the sonar speed. It's a speed that it belongs to the nature. It's not a coincidence. So it's not a coincidence that the sun is moving close to the speed of sound, and it always moves the same speed. So this is for some of those flat earthers who think that trying to save the AE map by saying that the sun is moving faster. It doesn't. Some of them saying that they staged it. No, they didn't stage it. They didn't. It doesn't move faster. It's just the AE map cannot represent the sun in the world. That's it. And the Glober's proven to you. That's it. So this is the whole thing about the AE and the 2P, two-pole, how they're different a little bit. Now I can talk about a little bit about the torus field, how the torus field looks like in the two-pole flat Earth model. And this is the only way that we can have a torus field in our model, right? A lot of you guys would have think that the center of the torus field is Polaris. You think that everything is going on Polaris, and that's the pivot point. Well, it's not. It's just yes, it is. It's just one of them. Okay, it's just one of them. But you have two of them. The Antarctica experiment told you that. We're telling you that it's two of these 2 points. On the globe model, they have them, but it's very physical. It doesn't it's a physical world that they made for themselves. No, they gaslighted with the globe thing that you have 2 points, one north, one south. But in the flat Earth model, we know it's a planar space. We have a planar space, and there are 2 points one under Polaris, the other one under the southern point, right? And by the way, some of the flat earthers also think that the A, you have that personal, like the Walter Bisler, the Shane's model. They still believe that you would have the people who go down there around the edge of the flat Earth, the AE model, they're gonna have their own personal sphere in such a way that they will have their own southern sky. They will have their own southern, that's very crazy. It's not like that. It's not a subjective thing. It's not like that every person goes around this AE edge map, the edge of the AE map, and he would have experienced his own southern world, his own southern star, his own southern sun. every person would have the sun go around itself on the winter solstice. No, it's not that. Some of the real and Shane's kind of provided an animation for that. That kind of shows you that. But the problem with that thing is that, as I said, if you would have 100 people going around the edge of this AE map during the during the northern winter solstice, let's say the 23rd of September, which would be their summer solstice, the southern world summer solstice. If you would have had these 100 people around this edge, right? And if you look them from the top, and if you ask these people to show you the sun, they would show you a fixed certain point in the sky. They would not show you a different their own personal sun over going around them. That's not true. Don't think that's the case. That is not the case. The same way that everyone sees the sun as one objective sun going around the Arctic during the summer solstice in our world, in the northern part of the equator, in the northern part of the world during the summer solstice, we all agree, even the AE map agrees, that there's a single sun, the sun that everyone sees is going around the Arctic, around the North Pole, right? But some of the flower earthers would have think that when it comes to the south, it's going to be different. It's going to be like every person would have its own personal sphere thing. This is not how personal sphere works. We spoke about the personal sphere. Personal sphere is the limitation of your vision. You cannot see beyond that sphere. That's all telling you. We spoke about it. That as you move toward any sun, it will start to pop up because this is how your vision works, right? So making a Polaris in the middle of that dome, making a bowl, like a fish bowl or something, like, well, you can think like a biblical way or these kind of ways that some flat earthers love, but it's not scientific. It's not based on our it might be true, but it's not still based on the observation that we have. Because we know that if we move toward any star, any celestial object, that thing will appear up. Nothing stays on the ground. Nothing will stay on the ground as we move toward it. If we would have had this sealed domey shape around this flat Earth, you would have some stars that as you start moving toward them, they wouldn't come up. They would have stayed on the ground. So that would in that case, if you would have had that observation, we could say that that would be the end of the world. That would be the end of the firmament. But that's not the case. Any star, if you go toward it, it comes up. So your ceiling is going to look like this. This is the ceiling. One is north, the other one is south. The tropics, those are the red lines are your magnetic field. The blue lines are the tropics. Now look at here. Look at their model. We are using the same principle, but on a flat, planar, stationary plane. This one is not accurate. See, the one that is down. This is kind of a type of AE thing. You're just using a 1 point. You're missing half of your reality. The AE map has missed half of the raw reality, basically. But this one, see, you're covering everything with it. You're gonna let the sun to dance around, and it's gonna fluctuate. Here's the thing. Let me tell you about fluctuations in frequency. We know that everything is vibration. This is what Tesla said, right? Frequency and vibration. So you have to think in such a way that the sun is fluctuating on these two poles. The same way that the pendulum fluctuates, resonates, goes from back and forth, the sun goes back and forth. But the period is going to be 365 days. It's not going to be tangible for you the way that the pendulum swings, because this is a very long period. But it's a period. The moon has a period. All of them have a period. All of them are fluctuating. Things fluctuate when it goes back and forth, right? In the AE map, nothing is going back and forth, right? But in this model, the sun will go back and forth, right? We spoke about it. 6 months north, 6 months south. And about the equinox, we spoke that how this transition happens. Does it happen very harsh or very hard? It happens very smoothly and easily. Just go to that video and see how this transition happens. So you don't have a Pac-Man thing that you had in your mind before about it. Some of flat earthers, when they hear this two-pole flat Earth model, they oh yeah, we know that they're saying that the sun disappears. No, it does nothing disappears. Everything is going around either north or south. You can follow. They followed it. They followed the sun. So what happened in the Antarctic experiment 24 hours? They really followed. Really, they could have followed the sun for one day. If they would have stayed another day, they could have followed the sun in its whole course. And it's based on the two-pole flat Earth model because it's really going around south. You can if they would have stayed 1 week, the people like McToon and I don't know Elizabeth, if they could have seen that the sun is going around the north south pole for at least as long as they're saying there. So yes, it's going around it, but it's flat, but it's going around it. So it's obvious. Okay, guys, I think it's enough here. Like, if you have any questions, let's talk about it. But I think after that, we can move on to this part, the toroidal field. That why this model is the only model that really makes sense to look like a toroidal field. Do you guys have any questions regarding to things that we said? How many people are here? Am I audible?
No, we can hear you.
Okay. Yeah. So let's talk about the toroidal field a little bit, and then later you speak more about the other stuff, like the like how any creation that you see, like this owl, the face of a human, your heart, your brain, every living being, it's symmetrical. You have sort of a two center, like a human eye, which the left eye and the right eye, and the third eye, or your spine. If you don't believe in the third eye, I don't want to talk about it, but your spine, the middle is the equator. So you can look at Earth as a living being, look symmetrical. The spine would be the equator, right? And the north and the south pole would be his eyes, or his his hemispheres, or his like the atria and the ventricles of his like a heart. The atria and the ventricles are even your heart kind of works like that, right? You have these two sections. One receives the heart. Here is it. Look at this one. The sun, the atria receives the blood, circulates, and the ventricle pumps the blood out of your heart and just give it to your organ. So this is even how your heart works. You got two counter rotation on your heart, two parts, right? So we know that our heart has its own toroidal field, right? It has a toroidal field. We call it the magnet. Science called that the magnetic field. Well, all the magnetic field eventually, if you look at them, they look toroidal. They're all toroidal fields, right? So a magnetic field. So oh, model here. We'll talk about. Okay, Gio, I didn't hear what you said, bro. I think I don't know.
Oh yeah, sorry. I think my connection actually dropped out. Am I back now?
Cool.
Okay.
Okay, go on.
Yeah. No, I was just gonna say these are a lot of really good points, and all of these correlations. It's great to see all of this, and excellent work. So I wanted to ask, one thing is when you have like the southern rotation and then when it transitions to the northern, what do you think would happen if you were to go like all the way east on the equator? Like, would you be able to see, that it would be, starting to make that other circle? Like, would you be able to see, a day before the equinox, you'd see this, you'd
Yeah,
be able to
yeah.
follow it
Good
circling that way,
point.
and then the day after, you'd be able to follow it circling on the other?
Exactly. Good point. Right. So here's the thing, Gio. Do you agree that they have seen the sun going around the South Pole when they were in Antarctica? Do you agree with that? That it was making that that turning thing, right?
Yeah, the 24-hour sun
Yeah.
symmetrically and mirroring what happens in the north. Yeah.
Yeah. So you know that basically the sun is all like it's making its circle around the southern world, like from the summer solstice, from their summer solstice to the equinox. You kind of you can see like you're not gonna see it till like I don't know like February, but from September till March, like if you would be like in the south, pretty much the south, you might be able to follow the sun, right? The same way they have followed the sun for a couple days when they were there, but they were like why it was visible because it was the sun was making very small circles. Now here's your answer. You would be able to that, but the problem is that the sun during the equinox would make very big circles, my brother, and that would be very hard for us to following it. But if you stay a little bit like longer, and if you let the sun to get even making smaller circles, you might gonna see it. So it's did you get the point? Like how it's like it depends on how you can have access to those areas. So that would be
Yeah.
like the West Coast.
Well, I guess like on the globe model, they basically explain that by saying the Earth is curving. So they're going to say that the sun is, that the Earth is tilting, and therefore the sun doesn't have to necessarily arc off differently. It's actually the Earth itself that you're on, that causes that effect, basically, where the sun, based on the tilt, the sun would get closer to the equator on the globe, and then it wouldn't really have to curve off the other way. It would be actually the contour of the ground that actually is curving off in the northern hemisphere on a globe versus the southern, that is the ground that's doing it. So, but if having the ground be planar, and then the sun path doing that with a celestial sphere like that stereographic projection, then because the ground is not contouring to cover that, it now has to that contour has to happen in the sky, and then that's that question, what it would be. But yeah, I mean, being able to go and see ourselves, of course, and to observe that whole path, but I mean, if you're just going east, I mean,
Restriction.
conceivably, you're allowed to travel, on the equator, circumnavigate on the globe, if you have the equipment.
Yeah, exactly. It's restrictions that we have. There's some restrictions in our reality. We have, yeah, that's a good question. So you got a lot of, you got national securities, you got international securities, you got a lot of treaties, you got Antarctica Treaty, you got Arctic Treaty, bro. So these are the kind of things that they shackled us to just go and explore everything. But the least that we know that at least when sun is making smaller circles, either on north or south, we're able to following it. Right? This is for sure. So we know that it will circles around the south. At least we have seen it with our eyes. And we can feel with our eyes for a short period of time. Let's say from September 24, I don't know, to January 20, something like that. That would be visible for eyes. But beyond that, since sun would have made bigger circles, you would need more access to those areas to see it. But you need to see the trend or the how it's been like how it was functioning and how it was behaving before like the equinox. Before the equinox, we know that it's going around the southern point. So like the star trails, right? The star trails, no matter any star you pick up, in the two-pole flat Earth model or the globe model, eventually for the globe model, because of the tilt, it either, it either goes around the south or north. and also in some part it goes around. I mean, well, never mind. That's a little bit advanced. I don't want to kind of mess up with a lot of you people here, but later I want to talk about like why these zodiac signs are exactly kind of perpendicular to the Milky Way. Yeah, that that bright band that you see in the sky as Milky Way. That's kind of a little bit. That's kind of a perpendicular to this equator, right? To that equator. So you have a cross shape over there. Never mind. So back to the toroidal field. So the thing that we had about the torus field, the Polaris was the middle of the torus field. Well, that's not the case. Like for example, in this image, you always would have think that okay, the Polaris is that middle of this torus field, and that's it. Well, it's not. It's not like that. Torus field, it creates two lobes, like the sun and Lima, like the star trails. Look at this. Look at the star trails. You can see the two lobes here. There are two lobes. You can see the right and the left. Kind of a. The picture is not completed, but if you complete the picture, if you imagine that it was if it would have been a panorama image that you would have seen the 360 degrees, you could see these two rotations like this, like this. Yeah, this one is good. These are the movements of the sun, basically everything. So this is your torus field. This is your torus field. How does it look like? You can look at it like this way. Look at a tree. Look at the trunk. Look at the trunk of this tree. The trunk of a tree is the equator, or the equator is the trunk of. So because some of the flat earthers believe that Earth is a tree. Okay, so for the sake of those flat earthers who love to see the Earth as a tree, they can put the equator at the trunk of this tree. And if you look at the roots in the branches, it's creating these two lobes, right? It's creating them. So we're going to call them N and S, south and north. So this is how the torus field really looks like. Now, to be more assured of this, we have to come to a simple creation. Look at an apple. Look at this apple, right? So this part, I hope I can explain it very well because this is very important. This is so important. This is exactly how will help you to visualize the torus field and understand the toroidal field much better than you had before. If you basically can cut the apple from two directions, you can make a crosswise or you can make a vertical cut. If you make a horizontal like a horizontal cross, you will get this beautiful shape that you have a star. This isn't that beautiful, like a human body, a 5-point star in the middle of this creation, and you have the circle around it. So a lot of flat earthers are like, this is what we used to think that okay, this is Polaris, that beautiful shiny star in the middle, that's Polaris, and that's the flat Earth. Well, no, it's not. That you just look at it from the wrong direction. There's another cut. It's called the vertical cut that will give you this one. Now compare these two pictures. Same torus field. So all the things that you had in your mind that the torus field only has one center, yes, the torus field has one center. Look at the image at the top. The seed is the center of the torus field. When you make a horizontal, the crosswise cross section is showing you your toroidal field. That's the center of your toroidal field. But if I make a vertical cut, I get the bottom image, and I'm going to end up with these two beautiful golden spiral lobes. And they're golden spiral. The edge of the second image and down, if you look at the edge is golden spiral. Fibonacci, 1.6 radian. So this is where we're gonna relate this model to the second geometry. We're gonna use all the Hermetic's law basically. So far we covered a lot of them. We covered the first law is about mentalism, that we're living in God's mind. Well, yeah, we said that our sky looks like two eyes. The southern point and the north point in the sky kind of looks like this owl thing, or a creature, or any human body, or any living being. Look at this owl. Look at the eyebrows. Don't they look like these tropics that we spoke right now? The star trails. Look, just take a closer look to this owl. Just look at the middle. The nose is the equator, right? So I have to just flip it. If I flip it like this, how do you flip this? I don't know. Anyway, oh, here. Oh. Yeah, I'm not very good at this. Anyway, so if you just flip this, you're gonna end up with the what we were talking about here. You're gonna end up with a two-pole flat Earth model: north, south, one center up, one center down. The middle is important. The middle is the nose, is the third eye, is your spine. The spine is the middle. The equator is the middle. Is where the stars are getting concentrated. Is where the zodiac signs are. So this is you see, it's matching with a lot of things right now. Because in the two-pole flat Earth model, if you remember the star trails, remember this image, this image. If you draw the star trail, the zodiac signs, those 12 important. They are exactly equatorial. It means that they're above the equator. So it means that they're in the middle. So it means that they are here in the middle. Look where the nose and the spine and the third eye and the middle of the brain, the pineal is in the middle, and you have the symmetrical fashion, right? Left and right. And look at the eyebrows. Look at those circles around the eye of this owl. Look at it. See them? Same creation. You see, as above, so below. Here we go. Second law, correspondence, right? So the owl, here's the owl. Can you see the owl? Oh, this is cool. So we had this in animation. So this is later we're going to talk about this sort of a fractal thing, that how the space time kind of works into these polar vortexes. But a human heart, again, we talk about the atria and the the other part of the heart that pumps and sucks the heart to counter rotation. Let the let the energy flow to run away. So when the engineers of this world, when they wanted to make a firmament, they had this cosmic westward bias motion. This one. I don't have a good picture right now to play the video.
You think that's connected to the Sagnac effect and the ether drift or ether wind? Do you connect that with that the east to west flow of the
With
sky,
what?
and then the entire the way the Sagnac effect and the Foucault's pendulum, and why the Foucault's
Well, I have
pendulum?
to think about it. Yeah. Okay. Yeah. Let's go into the Foucault pendulum. Yeah. I'm going to cover the Foucault pendulum as well, because we're going to talk about the celestial spheres basically. So I think it's in. So before I go there, before I go through the celestial inertial sphere that causing the Foucault pendulum to move, or all the hurricanes and typhoons that we have. So before I head there, this is so important. Just take another look here. So the crosswise cross section give us the center. So the center is the equator here, which in the top, and in the bottom image that you have the vertical cut section, you can see there are two lobes. It looks symmetrical. You have kind of a two seeds sitting on this, and kind of both sides. Now, if you let the apple to grow, it will become like a human like a human head, like has two eyes, or any any creature basically. So a heart. So this is a heart. Just look at this apple from this side. It looks like a heart. Your heart kind of looks like this, right? So, but yeah, you can look at that. So here's it. Here's your golden spiral. Here's your seed of life. If you look at it from the top, you're gonna look like this. You got to speed up. If you just cross it, see beautifully. If you do the horizontal cross, you get the seed in the middle. But this is what I'm trying to tell you. You look at it here. This is the thing that a lot of flat earthers have missed. They always used to think the Earth like this. They always look their flat Earth from this perspective. But now we're here to tell them, look at it from this perspective. Now, if you do this, if you look at it from this perspective, the middle, here's the middle. The middle is the equator. You got two lobes. You can see the sun and the lemur already here. You can see the 8 shape. Here's the 8. You can already see the 8. The 8 is here. Okay, you can see it. Those two lobes. So it would be here. So that's the right. So you can look at the north and left, north and south, basically. Right? You can look at north and south, and that's it. You're gonna look at that way. So you're gonna look at it from two perspectives. The center would be equator, but if you make a vertical cross section, you're gonna end up with two lobes. So the right will be your north, and the left will be your south. Yeah. Now, so even this. So look at here. This is the apple, same creation. See, this and this is the same thing. And your face, and the heart, and this. See, it's all patterns. We're just working on patterns. As above, so below. Law of correspondence. Second law of harmonics. So the first law was we were in the God's mind. We could be. I don't want to get into that right now. It's not very scientific, but you can. It's kind of a little bit, off the topic, but it's the most important one. The second law was correspondence. As above, so below. As a within, so without. And it's true. It means that patterns, golden spirals, are everywhere. We know that the Fibonacci sequence is everywhere. We can see in the sky. We can see in the ground. So this is exactly what they never taught us in school, to just look for patterns, natural patterns, right? But we flat earthers, this is the old key. This is our key. This is our point. We're using these sacred geometry and patterns in our nature that are going to be repeated. So everything that I said so far was just all patterns. We spoke about the symmetry of the star trails. That was a one pattern, wasn't it? That is the code above our head. Every day we're seeing, and that's the code that they cannot manipulate it. And this is the reason I'm saying that just focus on the sky instead of the ground, because the ground, the flight path, they can easily be manipulated, right? The flight path is not based on like which points are closer. It's based on a lot of factors, like geopolitical factors, security stuff, a lot of things if the treaties that we have, there are a lot of prohibitions that we have. It's not a good idea to just study the ground. Leave the ground. Ground is it's stable, it's flat, it's stationary. That's it. That's all we need. Michelson Morey told us that it doesn't. So the ether drag that you're talking about, well, the ether drag was, they were trying to find the ether drag, right? In the Michelson Morley experiment, because they were saying that the Earth is moving into the space, so there should be an ether drag, right? But they didn't change. They didn't detect anything. So they said it just because we didn't detect the ether drag, the ether doesn't exist. And just imagine how stupid that conclusion was back in time. And we all know about it. I can talk about that later if you want, completely about that experiment. That that proves that the Earth didn't move. They didn't directly roll out the ether. They just concluded that the ether didn't exist just because they couldn't detect any drag. Why? Because they presumed that the Earth was moving into the space along with the sun and the rest of the things. Therefore, if the ether exists, we should have been able to detect it. So just because we didn't detect it means that ether didn't exist. Well, you guys presume that the Earth is moving, but if the Earth didn't move, if you would have presumed that Earth wouldn't move, then you wouldn't expect to detect anything. ChatGPT also admit that later. Anyway, so we talk about symmetry. Symmetry was one of the other laws. The other law of harmonics is polarity. Again, we spoke a lot about polarity. We say that, okay, our model is polarized as two poles. So we covered the first law. We covered the second law. We covered the polarization. We covered the patterns as above, so below, and the cause and effect. The rhythm. The rhythm is the periods that we talk about right now. The seasons, their periods. So it's all based on harmonics. So back to the torus field. As I said, the torus field, you're going to look at from two perspectives, vertical and horizontal cross sections. The vertical cross section will gives you this opportunity to observe the duality of your reality. Flat earthers have missed this point that they're living in duality. It's good and bad, left and right, up and down. I don't know, east, west, north, south, positive, negative, flat Earth, globe Earth, right? Red, blue. This is what they're doing to us. Yeah, they're running the show using this law. They know the laws very well. The people controlling us. Anyway, I think it's enough for now. We can talk about things later, like a little about the equations, but I truly want you guys to look at the video that I posted about, about this model. Look at it carefully. Later, we're going to talk about, if we have time, we're going to talk about the equations as well. This one that we brought up for our model. What are the equipotential lines, which are the tropics here? It's completely correct. We know that every magnetic field would have these lines. You can look that up by yourself. Just look for equipotential lines of a magnetic field. You're going to end up with this beautiful image here. Interestingly, this is the same thing that we see in our sky. It's the same thing. Like there's no difference. So that's the map. That's the map that is above us. Now just look at this. This is a 2D map, right? Now imagine perpendicular to this plane, imagine a vertical dimension or perpendicular to this plane. That would be the electrical field or your gravity direction, right? So later we're going to talk about that gravity and electrical field by this map or by this model, like how is perpendicular to the magnetic field, and even their globe. Just look at their globe model here. See, this is why their model is so accurate. They have satisfied all these things of electromagnetism that I said right now. That the electrical field and the magnetic field and the movement of the particle, all three perpendicular. Look at their model. The red lines are the magnetic field. They are perpendicular to those tropics. They have seen that in their model. That's what's accurate. Now listen to this one. The electrical field or the gravity is perpendicular to this model. You can see it's in the radial direction. If you just draw the radial direction of the sphere, that would be if you just draw the radius of the sphere and just let it coming out of the sphere, that would be vertically, that would be perpendicular to the sphere. So that line, which is gravity, and these two lines, blue and red, they're all three perpendicular. See that? You see that? See how much they're accurate, how much they're precise on their model? And we flat earthers weren't with this thing that we had before here. Like, are they perpendicular? No. Look at them. Look at the magnetic lines that you would have think that you used to think that they were real, like these red lines. And you have those tropics, like this is the Gleason, right? Poor Gleason. If he would have been alive, he would have been shocked. Flat earthers are using this, but yeah, just look at it. It's not perpendicular. It's not. But here it is. Look at it. Here it is. Because it's polarized. But this is not. Yeah, okay. I think it's enough. Like we spoke, like you guys need to think about things that we say right now, and just watch the video, and later we're gonna schedule more time with Geo here, and we're gonna get more through this if you guys like. Yeah. Any questions, guys?
Yeah, I got a question. How is the sun going in the opposite direction in the southern in Antarctica for 24 hours, and I'm in the northern hemisphere and I can see it?
Yeah. How does it go? So at the equinox, it will go through this pattern. Let me just bring it up. So yeah, like this. Can you see? This is the spring equinox. So it's down there, and it's not exactly like this. Is a little bit, very, very like a very sharp turn that you see here. It's just an approximation that what happens. It's just a rough, demonstration. It's not very accurate. But if you go to that video that I provided in minute 6 till minute 7, you're going to see how the transition is going to happen. It's going to be very smoothly. But if you just if you look at this image, but it will roughly look like this image that you see here. It will go through this transverse movement, and this is what it really does. Because look at the sun analemma. Doesn't it look like an H shape? Don't you think that it has to have that kind of a thing? It was somewhere in its path to move from one pole to another pole. Because if you look at the sun analemma, let me just put it up. Basically, it has two poles, and you need to cover that on your model. Otherwise, it would have worked very well. Like you would have had a lot of problems. So unfortunately, internet is not a very good place. Like just look at my look. Here's the sun analysis. Like no matter where I just see in all the websites that I bring up, you can see that it's always showing you one part is bigger, like this one, for example. Yeah. So summer solstice, June 21st. This picture has been taken from above the equator. So I don't need to even look at the location. I don't need to even have a GPS. I don't need to even just by looking at the sun analemma, I'm just telling you that the observer is above the equator. Why? Because the upper lobe looks smaller.
You know what never
Now, if
occurred to
I
me about the analemma is it actually looks a bit like a fish, doesn't it? You know, like the Jesus
it's an
thing.
eight, it's an infinity. It's an infinity. Later, we're going to talk about
Yeah.
in sacred geometry. We have the eight. We have the infinity. You have that. Probably you have seen that snake that is biting its own tail that creates that eight infinity shape. So it's a loop. It's a cycle. It's a fluctuation. Let's say how does a pendulum fluctuates from back and forth? It goes back and forth. So sun is kind of going through this back and forth motion forever. Infinite, and it's just showing you the infinity sign. Like that's why we chose the infinity. I don't know why the mainstream science chose that infinity based on what, but we know it's all it's all cults. It's all cults, right? All the symbols. Really had to have some meaning. So the infinity shape is telling you that the sun would be infinite forever. Would have cycled around these two poles and it would create like that eight infinity shape. So yeah, so that's the problem. Now, if you go to this, as I said, if you go to the equator, here's for example this one. Yeah, this is all from north. This is all from north. But if you go on but if you look at the sun analemma and the equator, you can just you can search it right now. And they purposefully they have, I think they have deleted these images. See, you can't find that. It's very hard. Oh, probably this one. Yeah, this one. Here is this one. Yeah, the symmetry is possible. So this sun element has been taken. This one on the left is on the equator. The other one on the right that you see is in north. That is the north part. This one is an Arctic. This was what you guys remember. I said that the sun element would have looked like an elliptic. So if you go on the Arctic, or if you go on Antarctica, it would have looked like this. As you start moving toward the equator, it will start looking like this. And if you hit the equator, it will becomes like this. Right? This is the reality. Oh, I found it. Here is it. Oh. So this is the inverted thing that we spoke. Yeah. And this is one of those things that flat earthers are not very good at it. Like, I mean, they haven't studied the sun analemma very well. Like, they still think that it's as a constant shape, but it doesn't. Yeah.
If you could post a video of that, I'd love to. You know, if you
Just
did you say you had a
hold on.
video on the thing as well? I don't know. I thought you did, but yeah,
Yeah.
I'm open to looking at a model, but to me, it's the Occam's razor. The least amount of assumptions is to say that it's far away and we're on a globe. That's kind of the way I see it.
You think that you're in a globe? You still think that you're in a globe?
Well, I've been looked into flat Earth for a long time. Yeah. I mean,
I think the curvature part is something that, like, I'm a realistic person. I'm not a really those flat earthers that believe like the things that a lot of flat earthers believe. Like I don't. I stick with with evidence and experiments and observations. Like, that's it. Like, about the walls, like about the underworld, and I don't know, Atlantis. I don't know, the dome, and the seven firmaments. Like, these are just, yeah. I'm open to them, but basically, my understanding is based on the experiments and observations. And by far, based on my experience, I didn't see any curvature. Uh, Unfortunately, I haven't seen it. So, by the way, let me just share this images from
maybe just
my
because it's really
community.
big.
Oh yeah, that's that's a good thing. Well, that's why flat Earth is a scientific topic, because it has the three things. It's something that is observable. You can observe the curvature. Uh, you can repeat your observations. Is observable, and it's debunkable. And what you say, you just completed this scientific argument that this flat Earth would have become a scientific argument by be by making it debunkable. And what you say right now, you made flat Earth to be debunkable, and you made the flat Earth to be a scientific argument because it can be debunked based on what you said. We can be in a much bigger sphere. In that case, the flat
No, I
Earth
didn't
would
say
be
that. I
debunked.
didn't say that. I didn't
I
mean
didn't
it's
say
bigger
that.
than they
You said
actually
that.
said it is.
So what? So what did you say? Sorry, I took it you wrong. I thought you
No,
said that.
yeah, I'm saying it's the
Mm.
radius of 3959.
You think that's okay? If you think, okay, let me just share this with you. It might be a little bit interesting. If I could find it. Sorry, I should have already find it. This is yeah. Here's it. Well, yeah. As you can see, 1,000 views. If you guys, I'm gonna share my channel with you guys, if you guys like. Let me just share the channel as well. So this is the image that we took like couple. I think it was 1 year ago. This is a very big mountain. This is a mountain. The height of the mountain is 5,500 meters, and we went to this desert. It's like the desert is about 300 kilometers away from this mountain. And we know the height of the mountain respected to the sea level, and the height of ourselves we knew with respect to the sea level. We were about 600 meters above the sea level, and the mountain height was about 5,500 respect to sea level. Now, if you put all these parameters, the distance, the height of yourself, and the height of that mountain, uh, based on the curvature of the Earth that we have, this mountain should have been obscured by the horizon completely. Only probably 20% of the last 20% of the top would have only be visible, not the rest of the whole mountain. But as you can see on this image, which let me just share with you here. So this is if you want to watch the whole thing is here. We can have a good quality from this image. So basically, yes, this is as you can see, the mountain is completely visible from 300 kilometers, whereas it shouldn't based on the Earth curvature. calculations. And it's not a refraction. How we know it's not a refraction because there is a road that it takes you from this desert to that mountain. It's a straight road, kind of a straight road. And what you can do, you can always during the whole way you can observe the mountain. Like you can go there, and when you start off moving from that mountain to this desert, you can always observe the mountain. The mountain is not going to disappear or appear based on any refraction or any conditions or whatever. So that's it. This is what we have, and we have hundreds other observations that will debunk the curvature, like the Chicago skyscrapers, skylines from the Michigan Lake, the I don't know, like the Toronto or the Niagara observation. There are a lot of observations. You have the Bedford River experiment. You have the laser experiment. There are a lot of things that it will debunk the curvature. So our problem or our issue is not the curvature. I think the curvature is something that all the flat earthers, I mean, all of them, we all concede on this point, and I think that will includes me as a flat earther because I'm literally a realistic person. I study a lot about world model. I did masters in engineering in aerospace. I know that's ironic, sounds a little weird, but that's the case. And yeah, I believe the geocentric model more than the heliocentric. So yeah, and this is one of the this is a good observation that we had. It proves the that from 300 kilometers you're able to see these mountains, whereas you shouldn't see them. Yeah. So and yeah, and this is another good video. Let me just play this video as well.
ببین آقا این الان این
I'm gonna start rotating the sky. Now this is what I did here. But unfortunately, this is not in English. If you go on my channel, this is in the Persian. But what I did here, I started moving the time back and forth, and when I do that, you can see that half of the stars, half of the sky is going around. As you can see, the left is north and the right is the south. So just watch the video a little bit, and you can see when I'm doing this, you can see that the whole sky is rotating around these 2 points. And I'm on the equator. The observer here is on the equator and is looking top sky.
الان خورشید داره حول جنوب میچرخه و این خورشید ببینید داره حول جنوب. این الان خورشید رو مداره. این مدار رأس الجدیه. ببینید این مدار رأس الجدیه. خب این مدار رأس السرطان اینور. خب تابستون خورشید از اینجا میاد اینجا. انقدر اینجوری میچرخه.
Yeah, Andy, when you asked about the 24-hour sun, you see how with that kind of sky layout, you would have the 24-hour sun, two 24-hour suns 6 months apart as two parts of that field, like in the one half on the one,
Yeah, I have that.
and then the other half, the other 6.
Yeah, right. No, I'm just but the problem here is that like the time cursor doesn't go that much long, but you can do it by yourself. Like you can just increase the increments, and you can just check it by yourself. And this is what I did here. This is a good experiment with the software that you can do.
The thing is, the other thing the TFE, I think, debunks is that it's a local, close sun. My point was that how am I seeing it in the northern hemisphere and it's going in the 24 hours in the southern hemisphere? A local sun couldn't do that, could it?
Well, but you're only seeing it. Yeah, of course it can because you're only seeing like if you're in the north and it's wintertime, you're only seeing a small portion of it because the sun will rise, in the south of east, and it'll make that very low arc, and then it sets in the west, south of west. When you're in the north, so you're only seeing that arc of it. The rest of it is the rest of its circular pattern. So you're only seeing like a portion of it, which is why you get the shorter days.
Yeah, I mean, it's definitely lower in the sky, but to me, it just doesn't make sense if it's in the south for 24 hours, and then I'm seeing it as well. It doesn't make sense on a planar surface. I mean,
well, like in Punta Arenas at like 53, they got like, what was it? Yeah, 17 or 18 hour, something like a 17-hour sun, and then if you keep going south, you get the 24. But if you're all the way up north, you're only going to get, a shorter, much shorter than 17 hours as the further you go north, which is the same when it's in the north for the people when it's doing a 24-hour sun. It's the same for people in Australia. or in the south.
که
It's
این
just
خط
reversed.
وسط و الان دو
So if
تا
someone's in Punta
مستقیم
Arenas, when the sun is doing the 24-hour sun in the north,
که در واقع دو تا اعتدال
they're
اینها.
also going to see it
یعنی که
rising,
من
in their
اینجا
case,
اگر
north of east and the
تغییر
north of west,
بدم
making that
رو
arc
می‌بینید
across the
که
sky
حالا
as a
اینکه
mirror
همه
to what we see in the north
ترانسلیشن
when we see the
ببینید
sun
الان
during our
قرمز
winter.
به آکواریوسه برنامه بیداره رفت
Yeah, I
ساجیتریوس
think I'm more of a
سمت راست
visual learner,
اسکورپیو
so I think I'd
یعنی
like to see it.
این
You know, like just a video of it. I know he's trying to show a video of it now, but I'm sort of still not quite getting it. I want to see like
اسکورپیو
almost
داره
like a god
الان
view, if you
کلا
will.
حول جنوب داره میچرخه
I was
Yeah,
gonna
این
say,
from
is
above.
there
اسکورپیو
oh, sorry, my
داره
bad.
کلا
No, I
حول
just said from
جنوب
above, like a
میچرخه
god view. Yeah, like a
توی این
whole.
مدل ناکن
If
اسکورپیو
that's
رو
what, yeah, to be able to see it from all angles,
میچرخه اصلا اسکورپیو
from
ناکنی
above and outside
اصلا به
and
هیچ
inside.
عنوان
But
دور این
yeah, go ahead,
نمیپیچه
Burdick.
داره دور این میپیچه
I was just kind of
حالا
asking on
امیدوارم
the
این دیگه بهتر
viewpoints.
متوجه
Like,
شده باشین اینجا
it's cool to see like these perspectives and everything, right? But I don't think there's. I mean, unless you're on the equator, right? You can kind of see that the rotations are, to your left or right, but there's nothing that definitively shows like those center points of rotation in one video. If there is, and I'm ignorant to it, I'd love to see.
I didn't get it. Exactly what you said. What did you say about the middle?
Well, like,
You're a
so,
little
like,
muffled. Yeah.
okay, hold on one second. It might be my headphones. Can you hear me now?
Yes, better. Okay, it's good. Now I can hear you very well.
Yeah, it's probably my headphones, bro. Sorry.
Yeah. No,
What? Yeah, what I was saying was like it's cool to see like these presentations and all this about like the two celestial rotation points, but like
Mhm.
I never see anything that shows them both simultaneously doing it like in an actual observation, right? It's always a demonstration or a video. And maybe there is a video out there that actually shows those observations being done simultaneously. Probably.
Yeah, I know what you're talking about. At least the Antarctica experiment was one of those observations. So what you can do, you can elaborate that observation of the Antarctica and what happened. You can just expand it to another day and another day after that day. So the winter solstice was the 23rd of September. Now, if you just that you can do this mind experiment in your mind. You said just thought experiment. You would have said, okay, if they have seen the sun on that day that was making a small circle, then the other day, the day after that, the sun would have made another circle, but this time it would be a little bit bigger, right? Because I don't know, you're a flat earther or a globe earther, whatever you are, but this is how we used to think, right? And so you already have that. You can construct that in your mind. Because look, as I said, you don't need to go. Look, I understand what you're saying. Say that you added a video that I can see the whole thing in its entirely. But if you as you watch right now in this video that I made, like with the software, it's impossible to show to you. Like when I was rotating the sky, I don't know that you see it or not. The sun was going below the horizon. It was coming up again. We don't have we don't have a flat Earth software, a two-pole flat Earth software to represent that. You know what I'm trying to say? But so we have to use the solarium in some level because the solarium, when it comes to the observation, at least in our celestial sphere, in our dome of vision, is correct. But it doesn't. But the rest of the things are not pictured or not demonstrated very well. So, for example, when I was moving up, when I was kind of if you see here, when I was moving this back and forth.
ببین اینجا الان قشنگ مشخص کردم براتون ببین اینجا الان ناکنی شما آسمان برادر من
So if you see the software, it doesn't allow me to see things below the curvature because this is how this software has been made, right? So I do understand your question. You're looking for a complete, very like a video that it shows you everything at the same time. But unfortunately, in reality, it's very, very hard to do that. Why? Because you probably look how much it took time for people to go to the Antarctica. So we would need to do it. We would need to repeat that, my friend, for 365 days.
Well,
So
I
you're
mean,
asking, did you
I
get the
was,
point? Like we have to repeat that experiment for 365 days, and we can build up the whole path of the sun. But here's my word to you: you don't need to do it all for all the days. As long as some of the days you know that how it behaves, what is the trend, what is the pattern. You can easily predict that what would the sun would have do without just having a
I don't know if I get your point, but like I've been to South America, so I saw the southern celestial rotation, and then I live in North America, and even traveled, to the North America and saw that celestial point of rotation. But I've never physically seen them both in the sky at the same time, and it's pretty obvious. Like even on the equator, when I've been to Mexico and Central America, like I can actually see some of like one of the videos that you posted was how you kind of see
Yeah.
how everything's coming at you, and then you have 2 points of rotation that you can't totally see, but you can kind of see them on the right and left of you. Like
You
I've
see
seen
two
that.
half rotations at the equator. You just see two halves. You see the
Yeah,
north, half of the north and half of the south. You're at
yeah,
the equatorial region of the celestial sphere. So yeah.
yeah. But like, yeah. So I don't know,
Why,
man.
why would you ever see them both at the same time? I mean, you see a transition at the equator. You just see half of them, because as you go north, the northern one rises. As you go south, the southern one rises. And when you're at the equator, you see half of each.
I, I,
Yeah.
I can understand that. I can understand that, but I cannot understand how they would be possible on a planar surface. Like it doesn't make any sense to me. I don't see
It's
it,
on the
man.
ceiling because it's on the ceiling. It's not like you. This is the thing. Like look at my image. The personal dome is this is why understanding the personal sphere is so important. Look, they never taught us in school. That's the problem. We're not familiar with this thing. But you have to become familiar that if you're going to the flat desert at night, it appears that the stars are touching the ground. But we know that they're not touching the ground. We know that. But it appears to be like that. And this is what we're trying to tell to people, to globers, to all the people, that if you're not able to see the both poles simultaneously because of the way that you see things.
What do you
But
mean? There's
truly,
Oh, sorry. Go ahead.
bro, no, sorry. So, bro, see, the sky is you can. So basically, if you go in a very, very flat, let's say a very big flat warehouse, which has it has a flat ceiling. Or
Okay.
if you look at the end of a tunnel, the tunnel, you know that the tunnel is completely straight, but it appears that it will come down to the ground and it will create that, that vanishing point. Any tunnel at the end of the tunnel, you're going to see is this a point. It looks like the frames are getting smaller and smaller, but you know that they're not getting smaller. This is how your vision works. Your vision would not allow you to see the both poles simultaneously in the sky because you're away from them. But as you move toward any of them, they will start to shift up and come to your top. This is so important. This is fundamental in
But
both
it's
models. It's not yeah. Go on. Yeah.
but we're
Go
not
on. Go
looking
on.
at the tunnel, right? I mean, we're looking at equidistant things, right? And especially if it's a flat planar surface, then we're looking at equidistant things, right? In the dome or whatever. Like that concept doesn't make any sense unless I mean, look, man, I'm a simpleton. I am not the smartest I am not the smartest dude. I'm not the brightest crayon on the box, but like I don't know. It just doesn't make any sense. And I could be wrong. So I guess my question is like, so
Mm.
am I looking at like a tunnel or converging, train tracks, right, over distance, right? But if I'm looking at something that's equidistant from like all around me, right, and let's just say it's a dome, then I should have the same. I should have the same distance for what I'm observing, and then on top of that, like it should look the same. But the only place that it actually looks the same is on the equator. It doesn't look the same in the north. It doesn't look the same in the south. And then if you actually go to the north or the south, it looks totally different. They're rotating in different directions, right? And you can see a center point of rotation on them. So I guess that's where I'm just trying
So
to get.
yeah,
But
go on.
Oh, you're good, bro. And by the way, I really appreciate your presentation. It's
No, yeah,
fascinating.
I can help you with this one. So if just imagine that you are in a stadium, a court. What would be the best place for you to look at everything at the same time? Wouldn't be
I,
that the middle of the court? That would be the
yeah,
middle of that stadium. Yeah, exactly. So this is what we're doing here, my brother. If we go in the north, we know that we cannot see anything in the south. If you go now, here's the thing. If you go now, this is that later. If you guys think about this, it will things will start popping into your mind. It's very, very accurate because when you go on north, like when you go on Arctic, and when you're standing exactly on positive 90 degrees, latitude positive 90 degrees under Polaris, and if you look at the sky, everything is going around Polaris. Everything.
sure.
It's
Yeah.
completely like yeah, exactly. And in the south, if you go in south, vice versa, you're gonna see you have the same pattern. You see that everything is going south. So if I would have been there and I've said, okay, so this is my world. I only have one pole. Everything is going around it. Okay, I don't need to go anywhere else. Well, you're just. This would be exactly if you would if you stand if you go in a corner of a stadium and trying to look at everything. Well, standing in the corner of a stadium doesn't it doesn't give you a good vantage point. You need to go in the middle. So this is what we're doing. We don't have anywhere to go. Like if I go in south, I'm gonna miss the half of the world. So the best way is to stand on the equator and trying to see the both things. And when you do that, you see, okay, they're symmetrical. Like the same way that your body looks symmetrical. Everything in the polarity. You remember that we talk about polarity in our nature. That everything has been polarized, positive, negative, right, left. I don't know, up, down, bad, evil, good, evil, whatever. So that's it. This is part of our reality. You got two centers. Yeah,
I mean,
that's it.
I totally,
Mhm.
absolutely agree with you. I totally do. If I'm in the center of the stadium and if I'm on either side of the stadium, I totally agree with that. And I'm like, I've been there and I've seen these observations. Like the videos are very clear cut, whether what part of the stadium that you're in. So I totally get that. I don't understand how that makes it a
Yeah, you got to
planar.
go in different parts. So exactly. So what you want to do is that in order to understand the whole stadium, in order to see everything on that stadium, you want to move all around the stadium and look out everything. So do it. If you do that, you're going to come up with a calendar. You're going to come up with a map of your sky, and that would be like this. This projection. Here's it. Sorry. The one that Geo posted. This one. Yeah. So if you go all around the world and if you look at the sky, and if you just because a lot of your views, like if you go around the world, if you look at the sky, your sky, you're gonna have a lot of common stars and common parts of the sky that will be the same, right? So if you just go all around the world and just add all those pictures, all your views together, in trying to see how they look, you're gonna get this shape thing. You're gonna see this or these star trails that we had here on the equator. Now, this one, yeah. So if you go like in north, you're gonna only see the things that are going around just around yeah, north and south. So just go around the world, go around this planar, look at the sky, and see how the star trails are. And if you just add them all together, you're gonna come up with one pattern, and that pattern is this. This is the pattern here. This one, or this one. This pattern. This is what you see. This is the accumulation of all the observations that you can have on the ground. No matter where you go, you're always going to have those two fixed poles in the sky, right? No matter where you go, there are fixed certain points in the sky that we have them. They're not arbitrary. They're not subjective. All things. Look, they're not. They're not like something that is illusional. It's not. It's just a fixed real points in the sky, which presents our polarity. You have them, and you have the star trails going around them, and you have the magnetic field, which is perpendicular to it. and it's all fit. They all fit together because these lines, these star trails, they have to be perpendicular to the magnetic field. They have to. This is how electromagnetism work. See, I can just do the. Let me just do the third. Sorry, it's a little late here. Okay, the right hand rule states that to determine the direction of the magnetic force on a positive moving charge. So the positive moving charge. This is the direction of the sun and the stars. The stars are the positive part. The stars are particles. These are the particles that are moving in our sky. They're energy points. They move within this quantum field, and later we're going to elaborate that. We're going to use this. Look, the ether bit the fabric of the ether bit that we're going to talk about later. It will tell you that how these these particles will move along with this curvature. So this is so here's the look at this one. Okay, this is what I was talking about all over. We're using this law here in this model. This is the law. You see, the motion, right? The motion and the magnetic field are perpendicular. And as you can see, you have another one, which is your current. Just that's your that's your gravity. So gravity, magnetic field, and the motion. So the magnetic field, the electrical field, and the motion of the stars or the charges are all three perpendicular based on the the right hand rule of the electromagnetism. This is how the fundamental brick of this model. But that would be later. I want to talk about this a little bit later because this is another topic to get through it. Yeah. So I think it was a good introduction for this. I hope people would have listened. You guys would have studied more about it. Trying to talk about it later with some of your friends or whatever you guys have and see what is their opinion and can discuss about it. I really want to know your opinions about it. This is a model that I've been talking about in some spaces. I went in Clubhouse. I present this model. Some of the other rooms that I went, some spaces. When I present this model, yeah, I can see flat earthers are kind of a little bit. Some of them become very aggressive, like why you have changed the Polaris, why we're not glorifying or worshiping Polaris anymore, and they kind of a lot of flat earthers kind of acting like lobers recently when I showed them this model. It's like they don't want to accept new things. And so basically, yeah, AE model is, I think that's a control position model. It's something that they want to make it the narrative of the flat earthers, which is not correct. Yeah. So yeah. So what is your opinion, guys? What do you guys think? Any comments?
Yeah, man, that was great. I really appreciated everything you brought today, and yeah, lots of good points. And so, yeah, I really appreciate you coming and sharing everything. And so, yeah, does anyone have any additional questions or comments to add in? One thing I was going to mention, one comment I would have you thought about the idea of, that the sky with the two poles, like, has anyone ever mentioned, I'm not proposing this or putting it forward per se. I'm just asking if you ever thought of this, in terms of, you have the sphere, you have the azimuthal, and then you have the stereographic, and, which one is correct and which one's which. You got the sky and the ground, and of course the globe says the sphere is the ground, and so on. And then there's the AE, which is, that sort of vertical projection of the
Mhm.
from north to south down on the azimuthal versus the east to west, which gives you the stereographic. But what about combining the stereographic for the sky and then the AE for the ground? Now, I know that would be strange because the sun goes straight at the equator, and then you've got GPs, and then all the issue with GPs, if it's because then it would have to like move or something. Meaning, if you had like the celestial sphere north and south would almost have to be unique for each person because it would have to rotate around the outside of the AE as you traveled. So I'm not necessarily talking about the Walter Bislin, like the little sphere. I'm not necessarily talking about that. I'm just saying the two pole, the stereographic sky with the AE ground. Basically, that's the question.
Yeah, I know. Yeah, you were trying to combine. You're saying that okay, the sky, like the stereograph, but the ground is going to be like that. Well, Well, to be honest, Joe, it wouldn't make that much difference. I think the sky is more important, as I said in the first place. Like the ground, like okay, you can say okay, you want to say that like the tropics, because as I say like the tropics, like uh, we can have different tropics. Like we can have a some sort of a different system, different coordinate system on the ground. Like the Gleason is a one, Mercator is a one system, Gleason is another system, another coordinate system. So yeah, we can have different things on the ground. You can wrap around any point. Like the AE is around north. You can do that as long as it serves you. If it serves you for circumnavigation, which it would, like the AE map when it comes to like above the equator, it will serve us. It's pretty accurate. Even the size of the lands are accurate because it's it's true because it's been wrapped around the North Pole, the lands, and that's true for the northern part of our reality above the equator. Everything is wrapped around that point. So of course, the AE map would have worked perfectly, precisely for some applications like probably I don't know seismic, seismology, or navigations, communications. Yeah, we probably have seen it there using it because it's pretty uh, it's very functional. But the sky,
Yeah.
it's not sky. Yeah, for sky, we cannot manipulate that. It has its own backbone up there, and can see that. Yeah.
Yeah, I thought that was a good point about, the azimuthal in the north, layout is just from the north. And like you said, it's accurate to the equator. It's interesting the idea you said that you'd almost have to make a second azimuthal from the south, and almost combine them or something in order to actually sort of map it, rather than just doing it all from the north. I thought that was an interesting point. And then also,
Exactly. Mhm.
and then just the
Exactly.
second thing, basically, because what you're talking about with the two pole model would be more like stereographic sky, stereographic Earth, because of the two Antarctica and the North Pole. So that's like stereographic ground and stereographic sky. The globe guys say globe Earth, and that they do their thing, but but then I was saying, but what if you maintain the AE ground with the stereographic sky? So it's just like the difference between is the ground AE or is the ground stereographic? We know the sky is stereographic for sure. The two poles in the center, we know that, but it's the question of is the ground stereographic or is the ground AE between those two?
Well, I think the ground, look, here's the thing about the stereographic. I think the stereographic is a combination of having those two. So you get the point that I said that, okay, we can have another AE map that it is specialized for the north, for the southern point, right? You kind of agree with that. Like that would be much more useful for our reality if we could have that. Like we have two maps, one for north, which is called the azimuthal equidistant map, and and for the southern world we can make another map, which is kind of another AE map, but it's for the south version. And if we can use them simultaneously, it depends on where we at. Now, here's the thing: just combine them together, and that's it. You will get the stereo. You will get both together. So this is what we did. We didn't do it. Like we just add them together. Like you just imagine that you have the both AE map, one specialized for north, one specialized for south, and you're gonna just combine them. You're gonna put them together. Gonna put them next to each other, and there will be it will be a shared area between them, like the middle. So the middle was going to be more like straight, more concentrated. That's why you have more concentrated star lines and everything is more concentrated over there. You get more life. That's why the tropics are more. You got more woods and jungles and animals in the tropics. What? Because that's where the mainstream is going, right? It's barren. North and south is barren. Like it's not nothing. The life is basic. It's in the spine. Your main parts, your organs on your body are exactly all your vital organs are in your spine. They're in the middle of your body. So the middle of the reality, which is equator, is the middle of this life that Earth has. That's why tropics. You have more life on tropics. So for your question, Jill, that would be that's a good question. So uh, uh, yeah, what you're just combining two AE map. That's it. So on the picture that
Yeah,
you
which
see in
is
my profile,
which in their
that's it.
model, I mean,
Yeah.
even in the globe model, they have their northern hemisphere, southern hemisphere, and there's even those maps that show it like
Thank you.
that. You know, they show the two. It's like it'll be like a flat map, but they're trying to say they're basically mapping the northern hemisphere on one side and then the southern on the other. So yeah, it essentially ends up being the two kind of hemispheres. Um, but yeah, it's just the
Yeah.
difference of whether the ground is AE or stereographic, whether the sky, and then I mean, like I said, the sky is stereographic. I mean, the sky is not AE, like if the sky was entirely an AE layout type thing, you would have just the, Polaris in the middle and then all the stars would go out from there and that would be it. It would just be a circular, concentric circles going out from the center, and then the south would look different if that was the case. There would be a different look. And I know some people have tried to claim,
Yeah.
well, it's perspective, and there's some different theories that people have tried to come up with. But I mean, the sky is, in my view, clearly stereographic. You have the northern rotation and the southern, and then the equatorial, at the middle. So, and then the 24-hour suns and all of that. So if we want to call it, in terms of that being like the celestial sphere that has that stereographic type of a coordinate that we view it from, and then it's just the ground. The question, yeah, because then the two-pole map centered at the equator, the azimuthal equal area centered at the equator, that basically gives you a 24-hour sun in the north and a 24-hour sun in the south when you base it like that. But then it's the question of, and that's basically like a stereographic ground is the way I was saying it, because you have the sort of, the Arctic and the Antarctic would be the two parts of the stereograph, and then you have the equator at the middle. So that's the question: is the ground stereographic,
So
or is the
yeah,
ground
I think
as
that
azimuthal
I think
equidistant,
the
and then the
ground.
sky would still be stereographic? But then that's what I was asking:
Yeah.
how, in terms of those two being
Yeah.
combined.
But I think that's so the terminology that we're using as a stereographic. Well, yeah, you can use a different word, like for example, the face of that owl. It would be a stereographic. So this is like this image, right? Can you see? You have a stereographic here. Look at the eyebrows. Look at those tropics. Look at the circles around the eye, and so this is a stereograph. This kind of looks like the stereographic. So I'm trying to say that don't look at it. Don't use the. You can use the word stereographic. It's a cool word, but like a lot of things kind of look like the stereographic. Like, look, for example, this apple that I brought up here. Again, this is if I start separating these two seeds, or if I let the apple to grow more and let these two seeds become more separated from each other, again, you're going to get that stereographic type thing. So the
Yeah,
stereographic thing is
because of
something that you
the
can see
magnetic.
repeatedly in nature. Yeah, even
Yeah,
the magnetic
exactly. It's the
field.
magnetic,
Exactly.
yeah, the magnetic flux lines, and it's that portion of a toroidal field. Yeah,
Yeah,
exactly.
yeah, yeah. So I think that the both sky and ground, I believe that they're both, kind of look like this polarity. We have the polarity, but as I said, the ground is not our intention. Like it's not our attention. It's just something. It's just a physical realm. It's flat. It's stationary, and I think that we can concede here. And the other parts are more important, like the sky and like how the focal pendulum, why the focal pendulum goes clockwise and counterclockwise, and like how this celestial inertial sphere upon us, which we call them the polar vortex. This is a word that I made for them, polar vortex. So You have a north polar vortex and a south polar vortex, and each of them have its own bias. So this image here, this one, let me just put this one. Here is this one. So if you look at here in this image, you can see the star trails. It's gonna be, you see the star trails is been transparent on this map, and you can see that the middle is kind of a straight. This is approximation. It's not like that. So the middle is kind of straight. North and south have their own rotation, and the rotations are counter. One to go clockwise, the other one go counterclockwise. And this is exactly how really things work. Like, later, like in the next session, I would have prepared some other, analogy for you that, like, for example, anything that like a cycle, like a tires of your car, like the circulation of the blood in your heart. There's hundreds of these examples that you can see in nature that it's made of a two counter rotation within the one field. So it's a one field. It's a one field, which is, we call it here in the cosmic water, which is moved from east to west. So this is another important thing in this model. As you can see, you have this westward biased cosmic water gradient. It means that why we're saying that is because, like, for example, look at this image here. If you remember, I made this image. Like, look at the direction of the stars, that how they move. So you can see that it moves from up to down, or from east to west. And this is something very observable. We see this gradient. We see that every morning we see the sun would rise from east to west. Stars rise from east to west. Yeah, but of course, if you get close to the poles, you're not going to see the sun is going. Sometimes the sun will move from west to east because it's making a circle. But basically, the gradient or the bias is toward the west. No matter where on Earth you go, you can always see the stars are moving around toward the west. The sun will move toward the west. So this is mainstream. This is the mainstream flow. We call
Yeah,
it the westward.
yeah,
Yeah.
exactly. That's
What
why
do
I
you think
connected
about the westward?
Yeah, exactly.
Yeah.
Well, that's why. Well, because they say the ground is rotating. Of course, they say that the Earth is a globe spinning on its
Oh yeah,
axis. And
yeah,
that's how they account for that motion of the stars.
yeah, yeah,
But
yeah.
I was gonna post this. If you see in the live stream one text, real quick, I just tagged you on it. But images like this that show that toroidal field, that flux that goes through the center, up around the outsides, back through the center, that kind of pattern. And
Exactly.
I've got a few others
Wow.
that show. I have one other I really like. I'll post too
Wow.
that similar to that, and
Yeah.
that's kind of that east to west.
That's it, bro. That's it. That's it. That's all it is. You have it. Oh, this one. These are nice. Now you can see the counter rotation here. Look, just look at the first image, the first one. So just look at it. You can see you have the clockwise and counterclockwise. You remember that I said that stars will converge and diverge? You remember I was in my speech, I used this word that from the east they will converge and from the west they will diverge.
Yeah,
Here is it. Yeah.
yeah,
So that's the equator. So the middle is the equator. So these are you can look at it as a star trails. These are the red lines on that stereographic thing that we had, or the blue lines. I don't know, the ones that are perpendicular to the magnetic field, right? So this is how they move around these two poles. And you're gonna put an N and S, one in the right, one in the left. You can see so this is the apple. You remember the apple? The apple, the vertical cut. The vertical cut creates those two lobes, those golden spiral lobes, basically. I don't know if you guys remember. So with the two seeds, this is it. That's it. It's the same thing. Just look at this toroidal. This is how the toroidal fields is gonna. So now what we did, we have much more deeper understanding of the toroidal. We're looking at the toroidal field more deeply. We're investigating the toroidal field precisely, and that will lead us to see that in a toroidal field we do have counter rotation. Okay, so that's in your sky. You're seeing it in your sky. It's there. It's up there. They're moving counter. One is go clockwise. The other one go counterclockwise. Yeah, this is how the toroidal field works. This is how your heart works. Yeah, these are
Yeah, and I
good.
think
These are
about
very
too.
good images.
Yeah, I posted a few
Wow.
more there too. And yeah, I think of it
Yeah.
too when you if you took like a wooden spoon and you dragged it through water or a paddle and you pulled it through water, you get that same effect too. You get the clockwise and counterclockwise vortexes on both sides of it. So like how you
Yeah.
get you just drag you can draw your hand or a paddle or a wooden spoon, anything like that through water, and you'll right behind you'll see there's the wake that's created, it gets the clockwise and counterclockwise rotations, which
Yeah. Yeah.
as well.
Yeah. Yeah. Exactly. Yeah. So okay, that's good. We're reaching this point that we are addressing this counter rotation in our torus field. And it's beautiful that we have it in our sky. And they cannot change that. So now you guys are gonna getting that the focal pendulum has a counter rotation. Because when you move across the equator, when you move below or above the equator, you're going to enter into a different celestial sphere that moves in a different direction, moves in a counter rotation. So this is the reason that why the typhoons, the hurricanes will not form in the middle. Because in the middle, which is the equator, you don't it's very unbiased.
Yeah, I've
Remember
got
the
some
chart
images.
trail?
If I could just interject real quick, if you see what I
Wow.
posted a few more, but if you see this last one
Wow.
I just
Wow.
posted, that's supposed to be the actual hurricanes. That actually shows it. That's supposed to be the actual data. Another one of these
Wow.
too, so you can actually see it, the two rotations there,
Yeah.
and just the patterns of it, and how it's clear in the center, and you get the clockwise, counterclockwise. So yeah.
Yeah. Yeah. You just
Now see,
nailed it. Exactly. These are
yep.
beautiful things. Yeah. Yeah. Exactly. The counter rotation, positive, negative. That's it. You have the sun and the lima. Look at the images. You already seen. And you gotta get it like chill. This is the thing. Like the more we get familiar with this model, the more things gonna fit. Like the sun and the lima would have been explainable here because we have two lobes. We have this transverse movement that we spoke about the sun. That's the thing that you see in the sun and the lima. That midpoint, right? So yeah, that's it. That's it. That's all it is. It's a polarity. It's a duality. We need to accept that. We need to include the duality in the flat Earth model if you want to if you want to have a better approximation. Monopole doesn't exist anywhere. Stop with that. Stop. Flat Earthers need to stop with the AE. Though yeah, Walter Brisler demand that small dome that every person would have. No, that's not true. That doesn't because that will create an illusional subjective sun or illusional uh, I don't know sudden point for every individual who goes. Well, that's not the case. The point in the south is fixed. That point, the center, the negative pole, or whatever you want to call it, positive. It's arbitrary. You can call them vice versa. It doesn't matter. But it's a center. It's just a center, and that center exists. Yeah. So yeah, that's it. This is how the flat Earth model. I think that has jumped to another level. And here's the thing, Jill. The more you're going to study, the more we're going to study about this. This is what I experienced within this last year. The things gonna more match to each other. You're gonna find more piece of the puzzles, and they're gonna fit more to each other. And this is gonna more happen. Like it's gonna, and it's very very close to the globe. Like, and trust me, globers hate this model. Like within this couple of months when I present this model, globers they just scream because they say, "Hey, you cannot do that. You're using our model." I say, what do you mean? This is not your model. Like, what do we? No, you cannot use that. That's a globe model. You just put in the globe on a plane. You just cheated. They really hate this model because they know like we can use this model to explain a lot of things, like the focal pendulum that goes clockwise and counterclockwise. And it's very interesting. Like, just tell me about the focal pendulum. So, like, you already probably know that, the star trails like goes counterclockwise on the north and clockwise in the south. But the things moves like other way around. Like, the focal pendulum above the equator moves clockwise, but the stars above it is moving counterclockwise. Well, this will make sense. Exactly will make sense. It has to be like that because if you sit in a car, if the car goes forward, you're gonna hit your seat backward. You're gonna go backwards. You're gonna hit your seat. So if something goes forward, because of the inertia, you're gonna go backward. So if it moves clockwise or if it moves counterclockwise, things below it moves clockwise. The same way that when a car goes forward, you're gonna feel that you're going backward the first second. So that's the bias. So imagine that you're stuck in the traffic and every couple seconds you have to just push the pedal. And if you do that, you're gonna feel that bias. So that's the kind of thing that it's happening up there. Constantly, that this inertia sphere upon us is rotating. So it will affect the things. It will make the things to go into a golden spiral fashion. The reason that the hurricanes make that golden spiral, is because of the inertia sphere above it. The reason that the focal pendulum in every swing, in every fluctuation, if you leave and focal pendulum is not different from a normal pendulum. It's just a pendulum that you're going to leave it to just fluctuate for I don't know, for one day. That's it.
Well,
So if you leave the pendulum,
the precession.
yeah.
So you would say that the difference, they claim on a globe Earth at the different latitudes it precesses differently. They claim because you're on a globe, but would you say with this that it will precess differently at different latitudes because of this magnetic field and the concentric circles, and how when you go to different latitudes you're going to get the different readings? Yeah.
Exactly, because of the polar vortexes. Exactly. So you just nailed it. As you move toward these poles, you're going to be more influenced by this inertia sphere up there. So of course your focal pendulum, the precision is going to be more. It's going to be higher. You're going to get a big variation. You're going to see more changes. You're going to see more biased because you're going toward that polar vortex. But if you stay away from it. If you go to the equator, you're going to be unbiased. That's why that's why the focal pendulum goes straight, because you're on the equator. You're so away. You're in the middle. You're in the equilibrium state, and this is where the satellites can go. Like later, we're gonna look. This model can cover the satellite motions, because the equator is where you have the equilibrium, and this is where you can put your satellites or anything up there to go forever. A free energy. They know it. They're using it. It's in between these two poles, in the middle, the equator, above the equator. That's where you have your satellites. That's where the focal pendulum goes straight, because it's not influenced by any of these two poles. But as you move toward them, you're gonna get into their trap. You're gonna get biased by them. So your focal pendulum, the precision is gonna be hard, much more. It's gonna increases as you move towards south or west. You see, everything will as we start studying this model and and it's not that much different from the model that we have. We just polarized the model. That's all we did. It's flat, stationary. We can have the walls around it. That's all it is. You can have all those things if you're because some of flat earthers are completely become religious when we talk with them. Some of my friends, my old friends, flat earthers, they have become religious. Like they have the Polaris image all over their house and their profiles, and they think that's the center of their reality. And no matter how show them these evidence, bro, just divorce the Polaris. There's another guy down there. It's called the Southern Point. Just give some respect to that. They can't see it. So that's very dangerous. That would have happened. But yeah, you nailed it. You about the focal pendulum, geo. Yeah, that's true. So the middle, straight toward the south, clockwise to its north, counterclockwise. And reversely, the things would have at the ground would have moved on the other way. With the celestial sphere clockwise, things on the ground move counterclockwise. The hurricanes go created in the counterclockwise formation because of the, as I said, the analogy was that when you're sitting in the car, when the car goes forward, you're gonna go backward in the first place. That's how it works. So those biases is just because of this inertial sphere that we have.
Yeah.
What do you
Yep.
think about it? It's way better than the globe. Go on.
Yeah, it's like like a well, if I use the word ether, like it's like an ethereal sphere that is, the actual the sky, and then even the medium, getting into that too, like the toroidal ether and a toroidal sky, and those have spherical qualities. Doesn't mean the ground is spherical. The ground is planar, but it has those qualities. I would agree in terms of the Foucault's pendulum and then the motion. I mean, they claim that the Foucault's pendulum doesn't precess at the equator, which I understand how they can extrapolate that into their globe model, because they're basically just using the spherical nature of the sky and the medium that actually is where we live in terms of the actual medium. They're just conflating that with the ground. And then they're using a lot of the same math for the ground, which is why they say, quote unquote, it works out. So in a way it works out in terms of the math, but there's issues in the assumptions that the ground is curving and that it's a sphere in terms of where they've transformed the coordinates in order to, assert, that kind of physical reality, that the ground is the thing that's the sphere, rather than like we're referring to, the actual gradient from the equator to the north or to the south. When you have the toroidal field and the nature of the Sagnac effect and how everything is moving, like you said, you're going to get that effect, that's going to have the spherical math to it. But that's the question. What is the sphere? Is the ground the sphere, or is the actual, sky and then what surrounds us in terms of the environment functioning, in terms of that, the actual motion, like you said, for that, like the westward motion of the whole sky and the whole system, and then the weather systems as well, the sun, the moon, all of that is making that motion, and that has a a certain geometry to it, and so those geometric transforms. So
Yeah. So, but to be honest, I never got what. I never understand the way that the globers are explaining the focal pendulum. Like you're talking about this virtual force that will be created. So they believe that so this is the Coriolis effect. This is the Coriolis force. The Coriolis force that they're talking about is this. This is a virtual force that is because the ground is moving. It will create that imaginary force that will let the things to just go backward, in the other directions. So to be honest, that's a little bit very. I never perceived that. I couldn't perceive that. Like how does it really works? Because to be honest, I don't think that they have done any experiment, or at least in school, they never showed us that, like how this virtual force will be created. But in our model, we already can see the inertial celestial sphere upon ourselves. We're seeing these polar vortexes. We are seeing these vortexes, and when we see vortexes, we're seeing that there's an energy there's a center, and that center is causing these things to go around it. Right? This is what we see in our sky. Now, the globers are saying that's because of that's the axis of the Earth that you guys are kind of observing this phenomena. But as long as the Earth is flat, and we know it's flat, in this cosmology, these 2 points will be two center of this fabric of space time that we are living on it, and is causing to space to go wrapping around it, and it's doing it because we can see the star trails. The more stars the stars are more closer to these two poles, they're gonna be more trapped within this celestial sphere. The same way that the focal pendulum, if you go exactly under, like Polaris or the other southern point, you're gonna get a lot of precision there. And it's gonna be accurate. It's gonna be exactly 24 hours and 360 degrees.
So so I think this model, by having these two gigantic polar vortexes, which is more is I think it's more tangible than the globe model. What the globe model is saying about the focal pendulum, right? Because if you look at the hurricanes, uh, I checked that out. Look, you've got these satellite images. I don't want to use the word satellite images. I want to use the whatever you want. But the weather, if you look at the weather images that they have, like you can see the hurricanes and the typhoons and how they move and what is their direction. And if you check that out, you're gonna notice this that uh, below the equator, uh, it's moving counterclockwise. And it's because the sky above it is moving clockwise. So I think this makes more sense than the what Globers are saying about that virtual force. And yeah, they have a math for that. I've seen their math. I mean, uh, yeah. Yeah, so this is a model I think that we should spend more time on it. I mean, I think like a lot of flat earthers I know, like they have worked or they're working on it right now. And I think that Geo, you got all the elements of this model, almost everything, because you have seen the video before, and I need to appreciate, that you are a very open minded person. Like because I went to other spaces, other admins of other spaces, they're more kind of a very dogmatic uh, toward the this flat Earth thing. Like uh, there were like a lot of these communities that when I present this model, I immediately got blocked. Like, it was like they felt I'm trying to like steal their followers or whatever, but it was like there was we just proposed this model, and this model is not proposed by like me or my community. This is like this guy made this. The first guy who came up with this model was called Michael Wilmore. If you search his name, Michael Wilmore, Wilmore, Wilmore. Yeah, if you just it's double L. Sorry. Yeah, I don't know. I don't know. It's one L or double L, whatever. But if you just search this name, you're gonna. Uh, he works in this society called FlatEarthSociety.org. It's a pretty old Flat Earth Society. You probably have seen it. I think this is the first Flat Earth Society that legitimately we had on the website. FlatEarthSociety.org. If you go right now on their website, I think they're in Portland. One of their offices in London as well. So and they have some images there. If you go to their archive, you're gonna find this two-pole flat Earth model over there. But it's just a projection. So he never Michael Wilmore never spoke about how the sun moves around it. Like what are the things that we covered here? He didn't spoke about it, but the layout of the map is there. Like it tells you that how he used 2 points to project the globe model on this map, and how is it different than the AE? So yeah, so he basically was the first person uh, to came up with this model, and it's not just a theory; it's just a projection. You're going to project the globe on a 2 point instead of a 1 point. So we're not making any magic here. It's not from the globe perspective. It's not. This is not a magical thing. It's just a projection, which apparently it's aligned with the reality that we see in the sky. So yeah, he was the first guy who came up with a 2 pole, but it wasn't seriously considered by a lot of flat earthers because of the control opposition, the mainstream narrative of the flat Earth is so strong in the world. You all have seen it. You all witnessed it. The 24-hour sun experiment that happened. That was a control opposition experiment to debunk the flat Earth. They touched exactly upon something that they knew that the flat Earth has a problem on it. No, the tropics and the basically the monopole, uh, the origin of the AE map, which is a monopole. They knew that it has a problem, so they uh, point that out and they made it to make it look stupid, so they can shut down the whole flat Earth community, which they were kind of been successful on it. I think they pretty much been successful. Because I've seen a lot of flat earthers, they revert back to the globe. A lot of flat earthers are not understanding the critics that happen. They're still within their dreams, like the AE map and the magical dome and all that thing. They don't want to. They still saying denying the experiment that it didn't happen. So yeah, I think they did the job. They did a great job. They just spread out all the flat earthers from which they separate them. But I think it's time for us to kind of, at least the flat earthers who are more genuine and are more open minded. I mean, we need to just gather these informations and try to come up with a better model to just carry on. That's it. Okay. So, G, I think it's enough for tonight. We can just do it for another. Yeah.
Yeah, man. No, sounds
Yeah.
great. Hey, I wanted to just to comment on that real
Mm.
quick. To what degree, just since you just mentioned that, to what degree do you think that was planned? Meaning, okay, so on the one side of the spectrum, here this is what I'll say. So let's say on the one side of the spectrum, um,
Mm.
the least conspiratorial side, let's say, would be that Gleason was just a man. He made that map. He claimed that, and then it kind of happened to be that others like Eric Dubé and other people kind of found some of his info and other things like that. And then the AE map was promulgated and passed around, and so on, and then just happened to be that it had that incorrect information about the 24-hour sun, and then people all kind of got on the wave of it. And then, of course, and then Will Duffy came along. Like I said, this is the least conspiratorial, meaning Will Duffy's just a regular guy. He came along. He has his own agenda wanting to do this, and then he takes them, and then, and then they went. Now, that's the one side. Now, on the other side, the more conspiratorial side, is that the azimuthal equidistant map was purposefully, placed there as a backup to the globe deception, and the not the flattersociety.org, but I think the original one that many people think is controlled opposition, because there's two of them, but I think it's the other one, where that was there as a purposeful, kind of sidetrack. And then basically the idea that it was like a 10-year plan, from 2015 to 2025, roughly, be a 10-year plan to kind of, like I said, now this is the most conspiratorial, meaning that it was a plan to roll it out, all the way and to push the information with, misinformation agents, about the AE map and that there's no 24-hour sun, to really push it, to really get everybody to follow it, and get people saying it. And then, and then this, of course, kind of speculation would be that Will Duffy would be maybe even some involved further to where, it was planned that at, 10 years later that they were going to take this trip and then try to destroy it. So I just kind of laid out the two dramatics, but what do you think within that? Like, what do you think about that?
Yeah, that was a good thing. Yeah, you say, yeah. So I think it's in between what you say right now. The least is more impossible than the first scenario. But I think it was a ground scale. It was in a ground scale, but but it wasn't that much conspiracy. Like they hired people, like they hired Duffy or McTool. No, they didn't do that. Like they knew that how it was going to work. They knew that there would be some flat earthers, there would be some people that will follow this narrative. So we will just do that in a long period of time. It will be a time that we will run the experiment with some other globers who are not even hired. We're gonna just make the narrative to go like that way. So I believe that what you said I think the reality, the scenario is in between what you say right now here. It's not that much conspiracy, like I don't know that they have hired everyone but I think that they literally pushed up the Gleason map as a flat Earth. I think they really like the government, the shadow government did that. I mean, the people who are controlling us. And why I'm telling you that is because for example, if you go on the Google app, if you go on the Android app or the Apple app, shop stores, you can find the flat Earth application, right? The flat Earth application is one of those, it has a very high rate. A lot of people have downloaded it. Millions, billions of people have downloaded, and that's the map that you can just download it from the Google map, from the Google store or from the Apple store. So you can by looking. This is like and I remember that you were saying that we have to look the detectives.
So when you get into a room and you see the knife, when you see the blood stain on the ground, you're just putting the pieces together. So when you're seeing that the AE map is being propagated by the system all over the net, and you have a lot of people covering it, like Eric Dubai, and I'm not saying that they're, I don't know, I don't want to, but I'm pretty like this Sergeant, David Sargent, I forgot it, Michael Sargent, I forgot it, that
Mark
guy name.
Sargent.
So I think that, yeah, I think that he's kind of, like, he looks very, very, he looks suspicious to me, right? That guy. But it's not like everyone has been hired. Like it's not like because this is like the Globers would have said to us, like you guys would have think that everyone in NASA has been hired, everyone has been paid off. No, it's not like that. They don't need to be in the whole narrative. They don't need to be in the whole part of the whole conspiracy. They just use people. They just use the propagations and the narratives, and they know how people would have go through because people are sheeple, and so you have to guide the sheeple and to do this and do that, and eventually things will all set together the way that they want. So yeah, I kind of think that the AE map was a map that was like Gleason wasn't he wasn't inside the conspiracy. Gleason used to live, I don't know, 200 years ago, 300 years ago, whatever. So he wasn't inside the conspiracy. He was a flat earther. He was a cartographer. He did the survey. But I think it was the system who used this map and put it purposefully on the logo of the United Nations and the, I don't know, the World Healthcare Center, all these organizations, international organizations. I think they purposely really put that map over there, and it's a good map, right? It's not a wrong map. And even the Globers are kind of saying it's a good map. It works perfect in some cases. And the Flat Earth is also that, and we spoke about it. It's a pretty good, accurate map when it comes above the equator. So it's not that much wrong, but it's not accurate. It's not complete. It's not the truth of our reality. So I think that based on what you say, you just kind of say it might be a minor conspiracy or a major conspiracy. I think it's a major conspiracy, but it's happened in a very bigger scale. Like they didn't directly hire people. They knew how this narrative would have go along. They just shaped it with some influence that they had on it.
Yeah, in terms of like search results and
Mhm.
ways to put information out that would be available. Like even somebody like Eric Dubay, when he started researching it, what did he find? And he would find that information, things like that. Whether some people think yeah, guys are actually some guys are actual operatives or agents or not. But even from the perspective that they're, I mean, I'll tell you, when I first one of the first times I started, I mean, I had heard about flat Earth, when I was younger as well, of course, but I never really looked into it too much until around 2004, 2005. And when I looked into it then, there wasn't very much information out there at that point, on flat Earth. So back in 2004, when you did a search and, that azimuthal equidistant, that was the map that came up. That's the first thing that, that was all over. So just from search results and what was available, that was going to be, the main entree, if you will, the plate Earth, that that was going to be what was
Yeah,
presented. So
yeah, yeah, exactly. Believe in that, of course. That we got to be more realistic. We got to be more uh like we have to look deeply. Like they're not gonna let us to just know the true shape of the Earth by putting it everywhere. It's not. If we believe that this is a grounds conspiracy, they're gonna have a lot of ways to conceal it. One is that just spread the misinformation out there. Let people just mislead people. Some people. Okay, so this is kind of a yellow information. Just spread the yellow information. So this is what they did. They cannot hide it from, like, if they would have come up with this AE map, that would be very very much more skeptical for all the people. It would have looked more suspicious. Everyone would have become skeptical about it. Like why they're not coming up with any flat like this, but they already have it. They say, okay, if you want to say that Earth is flat, you have to say it's going to be like this because they made it. They made it that this is the thing that the flat earthers believe into it. The Earth is flat. The same way that sometimes they have these images of this pizza shape around the sun, going around the sun, or a square is going around the sun. We probably have seen all those stupid images. So they have these things in net, and it's interesting. Like if you just search for a flat Earth map or flat Earth model on the net, you will end up with AE map. It's all AE map. You cannot find any other map except the AE map. So this is suspicious. So yeah, I think that they're using a lot of methods to just hide the reality. Yeah.
Yeah, those are all very interesting points and worth considering because it does seem at this point almost too good to be true that that you would be able just to go, in today's day or even in 2005 or 2010 or even before that and just look up, that they would just get that the true shape of the Earth would be just right there on your first search, when you type flat Earth kind of thing. So,
Yeah. Yeah. Exactly.
just that alone.
Exactly.
I mean, there is something
That
elegant, though.
alone.
I mean, there is something beautiful and elegant about that layout of the azimuthal equidistant, and the continents all coming out from the center, and it does work pretty well with the sun times, for the sun rising and setting, and when the sun is going to be, especially in the north, and when the sun's going to be at zenith, rising and setting, and so on. So there is some accuracy there. The real thing that would need to be done is to measure the distance between the southern continents to really validate. Like if you could, measure the distance from South America over to Australia, or from Australia to South America, and then from South America from South Africa, Australia to South
Hmm.
Africa, and then from South Africa to South America.
Yeah.
Those
South
distances,
America.
because of course on an azimuthal equidistant, those are going to be dramatically larger distances, whereas on
Yeah.
either on a two pole or a globe, they're going to be much shorter distances. So that's
Exactly.
really what would be needed to just one of the things is measuring that distance, and even if you didn't do it exactly precisely, even if you had a rough distance, because it's, thousands of miles different. So yeah, if that could be
Yeah.
just once and for all validated, that would, if the distances are not what the AE map shows, and that's it. It's just would 100%, AE map at that point would be fully
Well, it
falsified because
doesn't because
that's something
it's
with the
sounding like
ground. That's not necessarily the sky. That's the ground, right there. So if
yeah,
that
that's the
was,
ground.
or it would be
Yeah,
confirmed
I
if the
know.
distances, or it'd be confirmed if the distances were greater. So
Yeah, even if you would have confirmed that this is a greater is shorter, like as I said, like it doesn't change the way that the sky works. It only tells us how the ground looks like.
right,
And
right.
so yeah, so the Sydney Santiago really doesn't make sense on the AE map. It's pretty like it's a full diameter of that AE map. So it has to be a flight about more than the 20 hours, but they will go more than less than the 14 hours. Even it's not a direct flight. A direct flight would be about 10 hours. I don't know. So there's some conspiracy about the contest that that airline that goes directly from Auckland to Santiago. Contest, I guess, is the name of the airline. That yearly they go. There are a couple of flights that they will directly go from. Well, but some flat earthers are kind of saying that the flight will always get canceled. They're not going to make. But even if we don't, even if we roll that out, we do have some other flights that it will take you from Santiago to Sydney or Australia, like in less than 14 hours, 13 and a half hours. And that it's something that it cannot be explained on the AE. And the problem is, again, is because the tropics becomes bigger on the southern world. So the globe is more active. So we need to be more vigilant, like more vigilant. Like we need to be realistic, more realistic. By when the globe model is kind of a look symmetrical, and the tropics in the south and north are the same size, like they cannot make this lie. Like this cannot be like okay for the curvature. They can just conceal it. But when it comes to these tropics and the circumnavigations that we have in south and north, I think they couldn't hide this. Like if the Tropic of Capricorn was really bigger of Tropic of Cancer, I mean, I think it should have been already revealed that. I mean, at least some salesman or some pilots, some private pilots, some people probably have been already exposing that there's the tropics below the equator are bigger. But nobody has ever addressed that. Nobody has ever experienced that the tropics looks bigger on the south than the north. And I think that's the part. That's the problem. I mean, that's the main difference between the AE map, the two pole flat Earth model, or the globe model. Because the two pole and the globe, they're exactly the same. They have the same counter, the same tropic. The tropics that you have on the globe exactly looks like the tropics that you have the two pole flat Earth model, but on the plane
So yeah,
instead
because
of having.
because you have because on a
Yeah.
globe you have the northern hemisphere and the southern hemisphere, which are generally equal in size, and you could project either one of those hemispheres onto an azimuthal plane. So if you made the northern hemisphere of a globe or the northern hemisphere of a two pole on like an azimuthal plane from, let's say one of them, an azimuthal plane from the North Pole, and then you have another one, an azimuthal plane coming out from Antarctica.
The south.
Yeah,
Yeah.
exactly. Then you essentially have the two pieces, those two azimuthal planes essentially that would be
So it's a two
kind of laid out,
azimuthal.
which
So this is
correlate with what they claim in their in their hemispheres.
yeah,
But
yeah,
and then you have that symmetrical nature though. But on a plane, it would just be like you said, like the eyes of the owl, like the face of an owl with the two eyes. Like you would just have those two regions. So yeah, it's sort of transferable again from the northern hemisphere claims of the globe, but basically putting that on a plane, like in that kind of
yeah,
figure eight type pattern.
yeah, exactly. So the so you can look at that way. You can say that the two pole flat Earth model and a one pole. So let's call the AE map one pole flat Earth model or monopole flat Earth model. So the two pole flat Earth model, the only difference is that you're going to project around two centers. You're going to give those tropics in the south to be projected or go around in southern point. So it would be like, as I said, you would have the both projection, one around the north, the one around the south. Let's say, as you said, based on what you said, you have two azimuthal equidistant, one projected around the north, one projected around the south. And these are my two azimuthal equidistant maps that I have, and they're both flat. And I have both of them. And I can use any of them, depends on where I'm standing. If I would be below the equator, I should have used the one that is around south because it would have given me more accuracy in terms of tropics and size of continents and everything. And if I'd be in the north, I would use the northern azimuthal coordinate map. So what I'm going to do is that instead of just choosing any of them, I'm going to combine them, put them next to each other, like you're literally putting them next to each other. It would be like this image. Let me just show you, this one.
And then that was a good point you said about the greater distances in the south that would be known because yeah, I mean you can even just on a private boat, a yacht or I mean it doesn't have to be a multi-million-dollar, although if you're going to go across the whole sea, you got to have something equipped to do that. But you could go, a private travel that if you wanted to, if you had the resources and the equipment, you can go from the western shore of South America, let's say near the Tropic of Capricorn, or even south of that, and you can travel across the whole Pacific. Now, I mean, that's the question: who's done that? Who has documentation of it? But I don't think that's like that I'm aware of. It's not like that's all off limits or anything. So I mean, there's people with private yachts, private boats, traveling. So unless someone's going to claim that that's all off limits, or you can't go
No,
there,
these
or
are
there's people with,
circumnavigate.
or
Yeah,
there's
that's a good
military
point.
with guns or some other theory, you can travel that. And so yes, like if that distance was greater in the south, like you said, seems like that would already have be well on at the very minimum commented on, noticed. To hide that would be is that even possible really to hide that?
Exactly. Yes. Yes, you nailed it. And this is so important. Like Jill, what you say right now, that these are so subtle things that flat earthers need to understand here. Like not everything is conspiracy. You know, like exactly, they cannot hide these kind of things. These are at least it would be a comment or something, and all these people should have already talking about it. And you nailed it. So this is how much you're smart to discern the things that what they can hide, what cannot they hide, like the weather patterns cannot be hide, like the day length. Like I was telling some of the flat earthers, okay, just go check out the day length on these websites. It's called timeanddate.com. Just go there and just choose your location anywhere that you want and check out the day length and see the symmetrical pattern of the day length across the equator. I was telling them, and some of these flowers told me that no, we don't trust these websites. We don't trust their data. And I was telling them, bro, it's not. Look, you cannot. Look, the stellarium cannot trick you. Stellarium cannot lie about the sky. Okay, we know the stellarium is based on the ground is being curved. So in the stellarium software, if you zoom in on the horizon, you will not be able to see the stars, which has been vanished on the flat Earth model, because it's the software has been designed in such a way that it will kind of hide those stars, because it will. It's been designed that they're below the equator, below the horizon, so they're not going to be visible. But you know that in your reality, if you would have been able to zoom on the horizon, it will bring more stars in your view. So about the ground, that's the problem that the Stellarium software has. But the thing that you see in the sky in the Stellarium software, the location of the stars, those are all true. The celestial sphere that you're going to create in the Stellarium software is true. And how we know that? Because we can check it with the sky. You can just bring a stellarium. You can go out tonight and you can check like where is the location that the sun is on the stellarium software, and check, or the moon, or the rest of the stars, or whatever you have in your view, and check them with the reality. And so you need to understand when an application has a 4-point star, it means that like a lot of people kind of check that. Like I did that 1,000 times. The first few times that I would use these softwares a couple of years ago, I was so interested in how they're showing us the exact location of these planets. Well, they're using our GPAs and our accelerometers, and so it's just an application. And it was true. Like when you hold the phone in front of your face in the sky, you can see the simulation. So you can see like the moon, and if you put your phone in front of your face, you're gonna see the virtual moon on your phone, and it's the same location. So these websites or these softwares, they cannot trick you all the way that you think. So timingdate.com, which gives you the day length, the sunset time, the sunrise time, the twilight time, they cannot lie these things. These are things that we can verify. Every person can verify that, right? So like some of the flowers were saying that no, the things in the south has been fake. We don't have observation of, I don't know, northern lights in the south, or I don't know, we don't have a southern point in south. And I was saying that, bro, we got people living down South World. We got people. We all probably have a friend or relative in Australia or in Argentina, or you can find a person on Instagram who lives in Argentina or in Australia, and ask him some questions that, you guys see the southern star? Do you guys see the sun? And if you do, so these are the things that they cannot lie about it. So if they're seeing that there's a winter down there and there's a summer up there, that's true, because you can call a person and see what they wear, or you can just travel there. It's going to be winter. Yeah. So this is very delicate. Like as a flat earther, you need to have this capability to discern that what type of a thing they can lie, what type of thing they can hide, what thing they cannot lie, and use those things that they cannot lie. One is the counter the things in the sky that we see, right? And the other things is the information that we can have, like the coordinates of the stars, the coordinates of all the celestial bodies. We can have them. The software is all accurate about it. The day length, the sunset time, the sunrise time, the locations, the tropics. These are all accurate. They cannot lie about this. But the flight path, as I said in the beginning, like the flight corridors, these are things that they can hide about. Even the pilots, they don't know where they're going. They just go. They're just following some coordinates.
But not the
They're
flight
not
time,
doing
because passengers know how long it takes.
Well, passengers can understand that. So a lot of the flight path, it doesn't make sense. Like in the globe model, we know that a lot of flight path doesn't make sense. Like from going
No,
from
on the globe model, they all make sense. I'm saying the flight time. Passengers can verify the time that it takes.
Yeah, of course you can verify the time, but they cannot verify the direction.
Right. They don't know for sure.
They don't know for sure, and it's all about circumnavigation. So the flight patterns, it's so the corridors of the flights are they're influenced by a lot of factors. One of them, you got a lot of treaty. We know that they don't fly over our Antarctica, so they will prevent to go there. So they will choose another corridor.
Yeah, they
Or
don't
there's
fly
some
over war
geopolitical
zones.
issues. Or
Yeah, they don't fly over war zones, and they don't fly too far away from places to land. So that's why they avoid Antarctica, because there's no place to land there.
yeah, but there's some countries that their airspace is closed for some other airlines or some other countries,
Right.
so they might gonna go over there. Yeah, so I'm saying there are a lot of factors that is there, and we cannot rely on this flight path to understand the map. And as I said, it's not important as long as it's flat. So you need to get on the airplane to understand it's flat. You have a lot of experiments that it shows us it's flat. So as long as it's flat and it's stationary, doesn't move, that's enough for us. Like we don't need to just dig into it more. Like how the flight path or why that flight takes 12 hours, why the other one takes 10 hours. We don't know about the flight paths, to be honest. We don't know about them, really. We don't know about how they go. There are a lot of things that will affect the flight path.
Well, it's true in a way,
So
Matthew. Would you even agree? I mean, you're relying on data you got from the internet ultimately, right? Like, I know people can take flights and do timing, but I'm saying to say that they all work perfectly, or to say you understand how exactly what part of the Earth they're flying over at exactly what speeds and exactly which way.
Yeah, I'm saying that it matches the globe. Like there aren't any discrepancies between what they claim and what the paths and the time
Yeah, there wouldn't
and
be if
distance.
it's pre-cooked. If they've already cooked the books
Right.
before, that would
Yeah,
already
it all matches.
Yeah, GPS. They have GPS, so I mean, you may think there is a globe, but if you consider not a globe, then I think you've agreed in the past that there would be a deception around this flight path scenario, right? If the Earth isn't
Right. They
flat.
would be flying non-standard paths, or faster than they claim, or slower than they claim, or going farther than the fastest way. All those things they'd have to be doing.
But remember, we're only talking about the southern flights. We don't have any problem with the northern flights. The northern flights are going to work with the Gleason map perfectly. Okay, so half of the flights, which would be probably the 80% of the flights that humans have, is happening in the north part of the world. We don't have any problem with that. Our problem is for the 20% of the flights that is it happening in the southern world, which we're saying that the corridors that they're taking is going to be affected by a lot of factors. One of them is the treaties. Okay, the other one is some airspaces that they're going to go around. It might be some military space. It might be some spaces that they want people. They don't want people to look at it. Like so it's not about the shortest possible time. You cannot make a straight line from one city to another city and say that okay, this is going to be my flight path. First of all, it's going to be a great circle, and your great circle is not always going to be the shortest circle on the globe model because, as I said, there are a lot of things that it would affect it. So basically, we don't have a problem with 80% of the flights that happens above the equator. The two-pole flat Earth model and the AE model are same thing when it comes to the above the equator. The movement of the sun, the flight path, the shape of the continents, everything is like the Gleason. Everything is like the Gleason. So I can say that if I'm a two-pole flat Earth model, or because I'm just for the sake of just being living above the equator, I would use the Gleason because Gleason would be a good approximation. And that will handle all of my life. So that's why the Gleason has become the most famous map for the circumnavigation. But the 10% of the population who live down there, we don't have a lot of, traveling and a lot of corridors down there. But if you would have, they would not be those straight lines that you think. You don't have that much enough data, my friend, to verify all those sudden flights. So I'm not saying that all the flights are completely being conspiracial and they're not going to direct. No, it's as I said, 80% of them are going to be completely like the AE or the globe, because the globe and the AE, when it comes above the equator, they're going to be the same. The great circle is going to be the tropics of the AE map. So on the globe model, the flight path would be a great circle on the globe. If you project that on the AE, it will be a tropic. You're going to have a circumnavigation around the north. 80% of the flights would be explainable the same way that is explainable on the globe for the AE and also for the two-pole flat Earth model. Now, for the rest of the flights below the equator, which is our crucial thing here, that we're going to talk about it, and we're saying that the conspiracy part is only here, not up there. So we're not saying that the whole thing is conspiracy, everything has been paid off, all the no, it's not like that. It's like 80% of the time, everything is true, it works perfectly. There's no conspiracy. But when it comes south, we're saying that the two-pole has these symmetrical tropics, like the north. The two-pole flat Earth model, respect to the AE map, has this feature, has this tropic patterns in the south, the same way that is in the north. It's the same. It has the same. They're same size, same shape. So this will help the flat earthers to explain some of the things that they couldn't. Not only about the rotations of the sky, the focal pendulum, and the 24-hour sun, which beautifully it can explain that, but also these flights that you're referring to in the southern flights, since these lands are, and this is what Gio mentioned before, in the two-pole flat Earth model, you have Australia and you have South America and Africa closer to each other, right? Like your globe model, which in the south they're closer. So your flight path, your flight times going to be shorter compared to the AE, which is correct. The AE map was wrong because this is what we're saying. This is what we are here tonight. We're saying that AE map in the southern part is wrong. The flight path is so long. But in the two pole, if you look at the map, the countries are more closer to each other. So the flight path is going to be shorter. It's going to be more make sense. So, and the other thing is that, as I said in the first place, this two-pole flat Earth model, if you look at the land masses, they're not accurate. That's just a representation of our flat surface. That's it. For example, you can take Australia. If you look at let me just put it on my look at my screen again. I'm going to put the two-pole flat Earth model here. So this model here, okay, here. Look at it here. So Africa is in the middle, Middle East is in the middle, America is in the west, Asia, China is in the east. So you have Australia in the southeast. So you can just pick up Australia from southeast and just put it in the southwest, and kind of shift a little bit the Antarctica toward the east. Nothing's going to change here. Like it's not going to change the two-pole flat Earth model. Its origin that there's two centers in the sky, and the sun goes around these two stars, these 2 points, creating a symmetrical pattern up there. Star trails are symmetrical with respect to these 2 fixed points in the sky. Those are something that we can see. Now on the ground, you can change anything that you want. You can pick up Australia from there and just put it next to America and make your flight path to make sense. It doesn't matter. As long as it's flat and stationary for flat earthers, we're going to move on to the other things. But if you want to stay on the flight paths, which I say it's not accurate enough for the southern world, we need more data. We need to study more about these treaties, where are the prohibited areas, which airspaces they're not passing over, and then we can come up with a better cartography. Okay, we're not cartographers. We're a flat Earth model. We think about we're looking at the Earth as an entire creation, its entire sort of origin, not the planar physical realm. So that's just the physical realm. It's planar. It's 2D. That's it. That's all we wanted to know about it. That's it. Yeah. So it's arbitrary. Do whatever you want with it. Change any continent anywhere. You just put it, make your flight paths to make sense. That's it. You cannot change the sky. We talk about sky. We talk about star trails, sun path. They cannot change that. That's symmetrical. Yeah.
Did you have a response to that, Matthew, or in terms of the flight paths in the south on a 2-pole?
Yeah. So I would suggest that wherever you put them on the 2-pole map, it's kind of like trying to fit a rug that's too big into a room that's too small. You might be able to squash it down in one corner and get it to fit nice and neat there. But then the flight paths on the other side don't work. And then you go over to the other side and fix it over there and move Australia over to this other corner, and then it works if you're going the other direction. So I would suggest that to get all of them to work, the globe map is the only map that I know of that makes all the flight paths in the southern hemisphere work correctly.
Right, I understand what he's saying, and that's true. but I'm afraid to talk about it here right now. I think it's a little bit early, but later, but it's about we have it's there's something called uh, the curvature of space time. Like, when you go from around these celestial spheres, well, basically the celestial sphere upon you is creating your space time curvature. And sometimes it doesn't look like the 2D way that we think. Like when you move from point A to B, uh, you're not gonna go in a Euclidean plane. It's the manifold of this model. It's a fractal form. It means that, like, going from point A to B doesn't appear to be like a straight Euclidean straight line. It curves, and you gotta reach it faster. Well, I know this is a little bit like, this is another like thing that later it's a little early if I want to talk about these things. But what you say right now, I understand. You're saying that if I move to Australia toward the south, things gonna work that part pretty much fine, but the other flights on the east, I'm gonna miss out with that. So, or you can think about finding an optimal location for Australia down there to making the flight path, the flight duration to make sense. I would suggest you to try that, trying to find Australia or the Antarctica. You can move any of them in the south part in such a way that the optimal way that it could have explains, or it will become closer to our reality. If you would have do that, Matthew, that would be, I would have appreciate that, because I would have need that data as well. I don't know if
I would
you
just
look
say
very
whatever
specific.
map you want to go with. If you like decide on a specific map, I'd look at it and see if I could find something that doesn't match.
So just do it on this map. What would be the best location of these three continents? The Antarctica, the Australia, and your South America. Like, how can you just put them such a way that it would have become closer to those data that you have about your flight duration? If
I
you
don't.
could do that,
Yeah.
and if you could share it with me, that would be possible. Because
I think it's
later I
impossible.
want to
Yeah.
use that. Okay, thanks.
I'm thinking from like Sydney to Santiago, and then Sydney to like Doha in the Middle East, and maybe Sydney to Johannesburg.
Don't
Those are
forget
like three different
yeah.
directions.
And don't forget that your circumnavigation for south is gonna be around your south pole. Okay, you already know that.
Right.
Okay. So, Gio, what do you think overall, like generally, what do you think, like, about this whole model?
Well, it's definitely interesting. We've talked about it over the months, and it's even before the final experiment. It come up at times in terms of that type of layout, because it's one that, like, if you go to like Wikipedia, the list of all the map projections, there's a few of them that have a structure like that. There's a few that have what that two pole type layout. There's a couple different ones. So yeah, it is very interesting. The one thing that sticks out to me about it is just like, if you were to go west on the equator, the globe claims you're going to come around the other side if you just stayed on the equator and kept traveling, directly west, just straight west on the equator. Of course, well, there's going to be land in the way, so you can't just make it straight. You're going to have to go over land, but that you would be able to circumnavigate the whole Earth, or if you flew an airplane on the equator, straight, that you would circumnavigate around. So that azimuthal equidistant map, attempts to solve that by making it a circle around Polaris. The globe, obviously, if you're on a ball and you're at the equator, then you're going around a ball. So with the two pole, that's often what I think about, is if you were to go west, what happens, and then that's why people talk about the Pac-Man. And I'm not talking about the
Yeah, this
sun.
is the thing. Okay.
I'm just talking about if you
Yeah,
actually
yeah, yeah, yeah.
travel. So that's
Okay,
just
let me just
something
explain
that,
it.
yeah. So like,
Yeah.
there's There is even an idea. Well, there's another idea that's not quite Pac-Man, but that it loops it's like an infinite loop from east to west. But anyways, I just how is that reconciled? Or like I think you mentioned you might hit a barrier. You might because like just lastly on an AE map, if you went west from South America, you would actually hit quote unquote the ice wall. You know what I'm saying? So like yeah. Well, I'm just saying on that map. So I'm not saying that's what it is. So, but you had said that you can't circumnavigate with the two pole on the equator, but that you would hit a barrier.
No, bro. Okay, here's. Okay, I love this. See, bro, yeah, that's a good question. You're saying, okay, so in this model, if I just keep going west, I'm gonna hit the wall, and I'm not gonna circumnavigate. But on the globe model, if you always be moving along the equator, I'm gonna always make this circle. I'm always gonna go around. I can circumnavigate. Well, yeah. So the globe model, if you would have been on the equator, if you start circumnavigating around the North Pole, you're always going to do this infinity circle around the North Pole, and that would have makes sense because that's our reality. It's true. Now on the AE map, it's the same. Look, if you look at the AE map, the tropic of the equator is just a circle, and if you start circumnavigating around the Polaris or the North Pole on the AE map, you're going to make a circle forever. Now your question is that, okay, what about the two pole? On the two pole, it doesn't make sense because on the two pole, your equator is just a straight line. It goes all the way to the east and hit the wall. But that's not the case. On the two pole flat Earth model, Gio, as long as you're circumnavigating, now this is I want you to just point this word. As long as you're circumnavigating, you're gonna always go around either these two poles. You're not going to go hit the wall. You can hit the wall the same way that you hit the wall on the AE. On the AE map, we know that if you would have go straight to the south, we would have eventually hit the wall, right? So on the two pole flat Earth model, if you go on the south, you're gonna reach the Antarctica. But if you go more south, yes, you're gonna hit the wall. Now, if you go toward the east from east to west, if you go toward the west from east. Let's say you're going to start moving from East Coast to West Coast. And when you reach the West Coast, if you still circumnavigating on the two pole flat Earth model, Gio, you're not going to hit the wall. You're going to go around the North Pole. So as long as you're circumnavigating on the two pole flat Earth model, it means that as long as you're going east or west, you're never going to hit the wall. And I understand where that comes from, why you're asking this question, because probably this part of this model didn't fit very precisely in your mind. That it's like the AE map. The AE map, you're saying that, okay, I'm going always toward the east toward the west, and as long as I'm on the equator, I'm always going. So what is your equator? Your equator is going to be always perpendicular to your compass. The equator on the AE map is always going to be perpendicular to the radius of the AE. And the radius of the AE is the direction of the North Pole or your compass. So as long as you're going to perpendicular to the compass, you're circumnavigating and you're going to make circles forever. You have the same thing on the two. So you have the same thing on the two pole. As long as you're always perpendicular to the North Pole, you're always going to go west to east, and you're always going to circumnavigate it. And you're not going to hit those walls.
Well, I hear you. So here, I'm going to post in the text real quick.
Okay.
This is let's see, is this from the Lambert? It's the
Did you get the point what I'm about it right now? Like,
yeah. So
I think that
yeah. So I wanted to respond by showing this image. So in that image, if you were a little bit north of Ecuador, let's say there's that latitude line that goes right through about Cuba, Middle America there and Cuba. So if you were to follow that one, I understand that idea that you would go up, like your magnetic flux lines would potentially lead you up around, because that would be the Pacific Ocean, but you'd be going, I guess, around the North Pole there. No, and so I get that, and then I get in the south, you would potentially be able to circle Antarctica the way the sun does and all that. In this model, the way the sun would in the north and the south, and you could circumnavigate just like the sun does. I get that. I guess that question again. So the sun could transition because it's in the sky. So of course, but right at the equator, that straight line there, that one doesn't curve up around. It's a straight line. So that's why I was asking.
No, that's an imaginary line. That's
Yeah,
it.
but
I
if you
should
travel,
have deleted that line.
no, but if you traveled on it, is what I'm saying. Like the sun, I understand the idea if the sun was,
That's not
transitioning.
circumnavigation. That okay? That's you just nailed it. So if you go just along that imaginary straight line, you're not circumnavigating anymore. That's not perpendicular to your compass anymore.
Okay,
That's
so
the
then,
point that I'm trying to tell you.
but
Yeah.
this is the main difference of this model and a globe is that a globe says you can circumnavigate at the equator going straight, whereas this one you would hit a wall, right? Is what you're saying, or what would happen if you just went
No,
dead
no, you're not
straight
gonna
on
hit a
that line?
wall. You're not gonna hit a wall. Okay. No, 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 no. You didn't pay attention. On the globe model, they're saying this is what they're claiming. They're saying that when we're going along the equator, you're gonna always be perpendicular to your radius of your model or the compass. So you're gonna always go to the west or east automatically because you're always gonna be perpendicular to the north. This is what they're claiming. Okay, so that would be in this model. That would be if you start going on the equator. If you be a little bit now, your equator is not a fixed certain line. As it's just a great. It's a biased thing. Look, those star trails that you remember that I showed you. If you would have been a little bit off the equator, like above the equator, close to the north, you're gonna make a big circle, big circumnavigate circle as long as you want to circumnavigate. If you want to get off the track, you're going to get off the track. You can hit the wall. The same, okay? That's the thing. But you're not circumnavigating anymore. So circumnavigation. Now this is how they indoctrinated us. You think that the equator is a straight line, and here's the problem, Gio. You're taking that assumption and trying to bring it in this model. The equator, okay, it's not a straight line. It's not a straight line. It's either it's going to be around north or south. We have seen that for sun. Sun would never go straight and hit the wall. It's either it's going to be a north, going around the north or south. It has to choose. It has to fluctuate in between these two poles. There's no third way. As long as it's circumnavigating. So you're saying that, okay, in the globe model, yeah, or in the AE model, we have a fixed, line that as long as we beyond that line and beyond that track, we're going to circumnavigate. It's always going to be perpendicular to the compass. But on this model, your equator is just a straight line. No, it's not a straight line. That's the imaginary line. You can just take that off and just have the equator like the trunk of that tree, which does not have a certain boundary. Like if you remember, the star trails, when they get close, they converge from east and they will diverge from west. So on the equator, they get closer. The same way the trunk of a tree, that the roots come up, they get close and they reach the branches and they diverge. So diverge from the ground, from the roots, come to the trunk and converge from the trunk to the branches. It goes back, circles around it. So as long as you're circumnavigating, as long as you're perpendicular to your compass, you would always go on your equator. So it would be like draw another look at this image that you share right now. What you can do, you can take off that straight line and bring it a little bit up, probably 1 degree, half a degree, doesn't matter. And this is like we're not working with numbers here. This is a reality, just very, very small interval. Bring it up and start circumnavigating. And in this model, you're going to go around North Pole. Now, if you come a little bit down and taking those star trails, the ones that are a little bit below the equator, your celestial equator, you're going to start circumnavigating around south. So you're going to have your circumnavigation the same way that you had on your AE, but it will depends on where you're standing on, and it's not a certain point. It a lot of factors, the wind, the fluctuation of the magnetic field, they will kind of change it, but eventually you would have circumnavigated. Eventually, the magnetic flux, the magnetic field will start telling you how to move to circumnavigate. Why? Because your magnetic flux is a curved line. It doesn't let you get out of the track. You would never get out of the track unless you said, I don't want to be perpendicular to my compass. I just want to go. I don't want to go west. I don't want to go east. I want to go southeast toward a straight line off the track. Yeah, you're gonna hit the wall in that case. The same way that you will hit the wall in the AE. But in the AE was crazy. The AE
I understand. Hold on, but I understand what you're saying.
Okay.
So you're saying there is a
Okay.
perimeter ice wall around this two pole, the whole thing. There's an ice wall around the whole thing, or a perimeter holding in the water.
That's a concept. Yeah, you can.
Okay.
Yeah, you can have that one. Yeah.
All right. So if there, okay, then that would be basically an answer to, because that, yes, and we've talked about that too. The idea that a two pole with an ice wall around the two pole. Now, if that were the case, I do now understand what you're saying. That there would be an ice wall. Therefore, if you went straight on that equator, you would essentially hit the ice wall, is what it would be, or hit a barrier, or some kind of a shoreline of ice of some sort, because there's not going to be enough sun to melt the water, and so you're going to have ice or whatever is going to be there. But if you were to follow the magnetic, like you were saying, in this model with the magnetic flux and the compass, either north of the equator or south, you're going to make those circles, which essentially is the Pacific Ocean on this. Okay, I understand what you're saying. So that eliminates any Pac-Manning or anything like that. So,
Oh, beautiful. You nailed it. Yeah, exactly. It's the bias. It's because of those. Remember, we spoke about those celestial inertia sphere up there, those polar vortexes. They are the reasons that are making this thing to happen. They don't let us to go around. If they're saying that, okay, as long as you want to be around, like perpendicular to me, you're gonna circumnavigate. And
right. I see what you're saying.
when you add, yeah, exactly. So that was exactly cool and I'm really happy that you found this bug right now in your mind, like, because when you that was this is what really happens to a lot of globers when they will they will bring those concepts from the globe model and try to bring it on the flat Earth, and it doesn't make sense. Even the problem here was that the AE also was kind of like that. Like, not the globe, but the AE had that fixed circle equator, right? We have the equator as a fixed tropic, right? That was the basically, yeah. So you were trying to use that concept here in this model, and that would have messed up even the transition thing that we spoke about, the sun, because the equinox is the crucial point in this model to people to understand it, that how the transition works, like the transition of the sun when the sun moves from north to south that we spoke right now, how smoothly it would have do. You're gonna do your circumnavigation on the ground would have be exactly like that. If you would be a little bit toward this north, you're gonna circumnavigate around the north. This is how the magnetic flux is gonna take you. They're not gonna go like forever. They will come. They will take you around they will take you to go around themselves. Or it'd be a little bit down to the south. The south pole will take you to go around itself. So yeah, that's it. That's the point, Gio. To be honest, and this is the point that it's to be. You have to be fair. Like, probably it will take time for people to understand these things about this model. And the more you're going to understand about it, the more you're going to see how much things going to match perfectly, especially about this Pac-Man thing that people have in their mind about this model. Like, one of the problem in this picture is that straight line that has been pictured there. So it's better to just take that off, delete that straight line, and making more concentric circles around these two, making more bigger circles around these two poles on this picture that you shared, and that will help the flat earthers. And those circles are not going to be exact circles. They're going to be they're going to be a little pushed and a little bit they're going to be tightened, more concentrated in the middle, like that convergent divergence thing that we said. Like a tree, like your heart, everything kind of looks like that. See? About the sacred geometry that I spoke of. So everything,
No, I hear you
matches,
on
to
that.
be honest. Like, yeah, cool.
No, I hear you on that, and that pattern of it. So another thing I suppose with this though is that when the sun does transition, like let's say you went um, from South America, you went west and you went all the way almost to the barrier, let's say, and you were just sitting there, meaning the widest circle of the sun in this kind of idea, where the sun it's still doing in the south, let's say, and it's making that the widest circle, and then coming very close to the equator, and then making a wide circle, and then a little closer, and maybe a day or two before the equinox, let's say, if you were in that, let's say about the 8 o'clock position on that map. Here, I'll just so people can follow along. I'll just repost it real quick. What the projection we're talking about. So just on this one. So if you went about like if like the face of a clock, if you went about the 8 o'clock position is what I'm referring to. So let's say you're about the 8 o'clock where you got the widest circle, or halfway between 8 and 9. So you got the widest circle and you're there, and then the sun is passing over you. And then as it's making these wide circles, and then it gets to the equator, and right at the equinox, it would transition to the north. I understand that idea. And there's a few animations I've seen of this too, as well, that some people have made. But so as it then goes to the north, you would then be able to be at like the 10 o'clock position, halfway between 9 and 10 on the north side of it. And in theory, one day apart, you would see the sun making the wide circle in the south, and then the next day, the wide circle in the north. And so with this type of layout, in theory, you could have like two teams, one team at the 7 o'clock position, the other team at the 10 o'clock position, and then one day apart, if you're on the outer edge of that wide circle, you should be able to see it one day, and then the next day you don't, and then the other guys see it going in the north. You know what I'm saying? As a consequence of this. That's another thing that would I would say would have to be verified to kind of strengthen this. If that could be verified by traveling there and viewing the sky in that
Yeah.
position, because it seems like that would be a consequence. At some point, it has to shift in that fashion. Because on the globe, they say that it's the sun, the tilt of the globe, and then the way that the sun is moving, and so on. That's how they describe it. But on this, it would have to transition from the one half to the other, and then you'd have to be able to see it making the wide circle in the south, and then flip the next day to the north. So that, what do you think of that?
Yeah, I got that. I got that. You're saying that if we would have two teams, like one at 10 o'clock, 8 o'clock at the equinox.
Yeah,
Yeah, that's a good
a
question.
day before and a
Yeah,
day after. Yeah.
yeah, the day before and day after, and so they have to see that time of. Yeah, they would see it, like it would, but it won't be tangible because it won't. They're not gonna see that much difference the day before that. Like if the people on the 10 o'clock, they're waiting for the sun to come over to just go around the north. They're just waiting for that. They're saying that okay, based on this model, like this is like today is 20 March. The sun is making this bigger circle. It's heading to noon. So right now we know is the sun that is coming toward us. Let's say it's 10 o'clock in the morning, and we're standing on the 10 o'clock 10 like 10 o'clock on this map, and it's 10 o'clock in the morning, and we know that it's coming up. It comes like 12 o'clock, it comes noon, and then it goes to our west. Now, here's the thing. Where is our west? The west, it would be around the North Pole, and it would set. So for us, it would be like probably we're going to see the sun that would have rise from east and goes to west. That's all we're going to see. We're not going to see anything else on the ground. It would have appeared from east to west. Now, the people on the 8 o'clock at the same time, what's going to happen for them is going to be like the sun is rising from the east and is getting away from them. Is getting away from them toward the west because it would be west for them, for the people holding the 8 o'clock. For the people on the 10 o'clock, it also would be west. For both will be west. That's the thing. That they would not notice this divergence. The divergence would not be noticeable. It's not possible to be detected that the way that you think that they would see a big transverse movement. We spoke about the star trails. The star trails are kind of parallel to each other in the center, Geo. So those, if you look at the star trails, they look pretty tight and parallel to each other. So this thing that would have happened, it wouldn't make that. You're not going to see a lot of difference. You need to understand that
Yeah,
the
because you're
sun path
also
is those.
you'd be seeing it within your own, the kind of personal atmospheric dome kind of thing. So you'd be seeing it within that too. So you're not really seeing it from a zoomed out perspective all the way up in the sky.
Exactly. This is where the personal dome understanding comes into picture. You're seeing within your personal dome. That's it. You not see the bigger scale. So even if the people would have been there and they've been in contact, the people in the 10 and the people in the 8 o'clock, and they're observing the same phenomena on the equinox, they're gonna see. They're not gonna see like a strange thing over there. They're gonna see that the sun is going to east from west. That's it. Because then they're in a very small their personal dome. Yeah, exactly. I hope you understand that because right. I mean, later, like when people come and like, because like, a lot of flat earthers would have come and talk about, the AE. And I hope that, you guys here actually understand some of the things on this model that it's possible to explain some of the phenomena that we have. And I believe that, I think that Geo, like you already got a lot of things from it. And I think you're going to concede on it. And this is not like the reason that we're calling it a two-pole flat Earth model is just because we're trying to make it different than the other model, which is a monopole. But it's a flat Earth model. It's not a two-pole flat Earth model. It's just a flat Earth model, and the flat Earth model has two centers in the sky, like the rest of the things in this reality, rest of the living beings, which look symmetrical. Look at your body. You just stand in front of a mirror. You can see the symmetry. You can see symmetry in the apple. You can see symmetry in the sky. You can see the symmetry of the focal pendulum. You can see the symmetry of everything with respect to the equator. And this is the most important thing that was missed by all the flat earth, most of 90% of flat earthers. And this was the thing that didn't let them to understand that the 24-hour sun would have happened. Like the ones who went down there, like they really failed to understand the simple, very trivial fact about the sun path and the day length around the equator, which is symmetrical. For example, if you're like positive 30 degrees above the equator, like I don't know, a city, if it has 12 hours, or let's say it has 8 hours day length, and the opposite point below the equator, you would have 8 hours night length. And vice versa. If you stay for another, if you wait for 6 months, you're gonna have a like 6 hours day length here and 6 hours night length over there. It's a symmetrical pattern with respect to the equator. So when you have 24-hour sun in Arctic on your summer solstice, you need to understand that it would have happened the same in Antarctica, which had happened, which they have proven to us. The Globers proven to us. We really didn't need to do that for us. We really didn't need to. They used that against us. Because we failed to understand the symmetry. Their model has a symmetry. The globe. It's just a pretty cool model that it can explain a lot of things, especially the magnetic field, the tropics. Apart from the topology, which is a sphere, everything kind of works pretty much fine in their model. So they really worked on that model. Okay, this is the model that it's the matrix model. So it's pretty accurate and it works pretty fine. So we have to borrow a lot of things from this model, and it's not a problem. It's okay if you want to do the cherry picking strategy. You can pick up anything from the globe model which makes sense and put it on the ground, flatten it, and see what happens. Okay.
Yeah, well, there's something to be said about the fact that we clearly see the two rotations in the sky, north and south, the two 24-hour suns, and then the equatorial, the stars going straight right at the equator, and then the sun at the equinox. So the sky clearly is observed that way. The globe Earth knows that. They model it by saying the Earth's a globe, and then they say the celestial sphere is a huge sphere that surrounds the globe Earth. Now, I'm not trying to go into that model, but that's how they claim it's laid out. However, on a planar surface, when you have those two rotations and then the center point, if the ground matches the sky in terms of ground positions of celestial bodies, consistent ground positions, of the sun, the stars, etc., it would just, and I'm not asserting this is what it is, I'm just saying that it would imply that the ground matches that two-pole stereographic structure of the sky because you have GPs. So if you have those GPs that are consistent, that's why when I mentioned earlier, if you have the two poles of the sky and then you have an AE map as the ground, you have a huge problem with GP positions of stars, which means you're not going to have consistent positions. Although there may be a way that actually, like with holography, with holograms, that you could actually, like the way that light could work, but that would be a completely different understanding of the sky. You'd have to imply that the sky is not, that there's not just consistent GPs, in a way that is of a sky, just like if you have the ceiling of a room and then the ground, the floor of the room and the ceiling of the room, that there's a relationship and there's, angles and so on that are going to match. So if you have a two-pole sky with an azimuthal equidistant ground, like an AE map ground, then you have to have something happening entirely different. Like you have to have maybe a holographic sky that moves with you or something, something that moves as you move. And then you'd have to have this sort. Hold on, let me just finish. Hold on. Then you'd have to have, I'm just saying it's the consequence of that geometry. You would then have to have that two-pole structure would have to rotate around the outside of the AE as you did that. So what I'm saying is that brings in a whole nother factor. Whereas the alternative to that is you have the two-pole sky and the two-pole ground, the stereographic, and they match. The question is that what the ground is? How is the land laid out? And then, some of these details we're talking about. But it is interesting just to think about the kind of logical conclusions of those two, kinds of ideas.
Yeah, exactly. You just nailed it exactly. So I was saying that, yeah, the stereographic thing that you talking about in the sky. As I said, I believe that the ground is exactly look like that. The tropics, the poles, I think they're the same thing. And as you mentioned, AE cannot work with the stereographic sky because you would have need that magical dome, like that holographic, I don't know, thing that would have happened, and that's not something that, like, where does that happen? Like, where is that point, or where is that air? Like, where is that tropic that if we start moving, down from that point, this magical, I don't know, holographic personal dome would have start being created, and that's pretty much easy to be debunked because it's not subjective. The location of the southern point is a fixed point, the same way that the Polaris is a fixed point in the sky. So that will rule out that holographic personal dome that we had before in the AE. Yeah, exactly, Gio. Yeah, yeah. Well, can't work. And we don't need to invoke these type of things like a magical dome and holographic. Like, and this is what they really want us to say. Like, then ridiculing the Polaris by saying these things, like these sort of things, which we don't need to. We don't need to just concede on that because, first of all, it's not observable. It's not like experiment. We cannot prove that basically. And so why not presuming that the Earth, the ground, and the sky are the same? They have the same counter, and the tropics that we see in the sky, which are the star trails, would be exactly the tropics that we can have on our ground. The GPs are exactly they're accurate, they're fixed points, and the globe model is, I think it's very accurate when it comes to the GPs. And so the two-pole flat Earth model is going to be like that as well. But for the AE, you need that magical dome to carry with yourself all around this edge of the model to, you know, that's, well, we shouldn't, like, I don't understand. Like, you need to agree that this is not a good explanation. When we already have this two-pole thing, that it's physical thing, it doesn't need anything to just explain it, and there's not magic, there's not something like reflection, like, because some of people would think that the southern world is a reflection of the northern world. Some of the flat earthers would think like that anything that you see in the south is just a reflection of the north. Well, it's not, because they're entirely different. They're entirely different constellations, and so, yeah, even that theory, it's not valid.
Yeah, definitely interesting, and that was a great discussion, and really appreciate all the just presenting all the information, and it's great. Yeah, we touched on a lot of points. Um, so yeah, are there any additional points, or if anyone has any questions or anyone else wants to jump in, feel free to jump in. But yeah, it's up to you how you want to proceed.
Well, well, there's a lot of things that we can still talk about, like, but we need uh have more materials for it, like the magnetic field, like the electrical field that it would have uh can be applied in this model, which is aligned with the gravity. A lot of flat earthers, they love about this electrostatic force to be replaced by to replace it to gravity, because flat earthers, they have beef with gravity, and though they believe that there's a bias toward the ground, but this thing that mass attracts mass, that's the type of thing that flat earthers don't believe. Even I'm not into it. I don't think that mass attracts masses, but the bias exists toward the ground, and that's this kind of a thing that's the thing that flat earthers love to use the electrical static force here to explain the gravity. Unfortunately, on this model, the two-pole flat Earth model, if you remember, we spoke about the right hand law. The right hand law in electromagnetism is telling you that you have an electrical field which is perpendicular to your magnetic field, as well as perpendicular to your to the velocity of your particle, which would be in this case would be the particle would be the sun and the moon and the celestial bodies on these tropics. So these three fields are all perpendicular. So the electrical field would be perpendicular to this two-pole flat Earth model, which be from ground to sky, and is exactly aligned with the gravity. So later we can use this force to explain some of the things that is happening, uh, as we call it, gravity, this downward force thing. That's one thing that we can talk about this on this model later. That would be a good point. And also sacred geometry. Like, we can invoke a lot of things from sacred geometry, the golden spiral, the Fibonacci sequence. We can use these numbers to find it in this model, like finding like the patterns that we have, the patterns that we see in the sky. We need to relate them to the sacred geometries that we have. And it is already related. Like, if you look at the galaxies, the arms of the galaxies, they are making a golden spiral thing. So yeah, these are the areas that we can work on it to making this model more. And I think this is a scientific model. Like, it's if you think like if you uh, study about it enough, and you're gonna realize that when you compare it with when you compare it with the AE map, it becomes more scientific. It is more aligned with the nature. It can explain a lot of things in the nature, as well as it's pretty scientific compared to the AE. Literally, it is more scientific. Yeah. Okay. So thanks for being here. Thanks, for the time scheduling. Let's schedule more time for about this, probably next month or next week or whatever. You guys are ready. I want to make more materials. I'm going to speak about the magnetic field and the rest of the things later.
Yeah, man. No, it
Yeah.
sounds great. Yeah, just let us know if you want to present again. And yeah, there's definitely a lot more, I'm sure, to go through, and like you were mentioning, those other topics too. So yeah, sounds good, man. I really appreciate the presentation, and and yeah, man, great work, and there's a
Cool.
lot to consider.
Yeah, there's a lot. Yeah, just if you had a time or something, just take a more look onto it, or and just trying to find questions. I really love to let's find some critic on this model. The more we find some critics, and the more we dig into it, we're gonna more understand about our reality. It's not about the two-pole flat Earth model. It's about just understanding our reality. So we're here till now. I think that I am here. I think that, like you, I think that you pretty much closer to your views have become so much close to me. So yeah, let's see what happens later. Okay, so I see you guys later, right?
Yeah, sounds good. All right, have a good one. Cheers. Talk to you soon.
Cheers. Yeah.